Hello and welcome to another tutorial. In this tutorial I'm going to discuss solving equations, and specifically one-dimensional equations that only involve one variable. And my focus is going to be on the real solutions, basically the solutions that are real numbers. So we have equations that are based on functions, real functions of real variables, and the solution that we're looking for is also a real number. So for different types of functions we can have complex or real solutions. For example, in the topic of polynomials, I discussed how to find all the roots of a polynomial, including the complex roots. But here the focus is real functions and real solutions. Okay, now what do we mean by solving an equation f of x equals 0? Now obviously we want to find solutions on a given interval. We don't want to search from minus infinity to plus infinity, right? So we are looking for the real roots of real valued functions over a given interval a and b. And we can assume that a and b themselves are not the solutions, which is very easy to check for, and therefore we can assume that the opening and the end of the interval are not inclusive, so they don't include the a and b. Okay, so one-dimensional functions are concerned only one variable. Okay, so I'm going to write it here, only one variable. We assume that the function is continuous and endpoints are excluded because it's very easy to check for the endpoints, whether or not they are the roots or the solutions of this equation. All right, so if they are, it's very easy to check, so we can assume that the endpoints are not the solution, so they are excluded. And we're going to also assume that the function is continuous, which means it doesn't have any discontinuity. It can be a function with the sharp edges, so it doesn't have to be a smooth function, but here we only assume that it's continuous, so there is no jump or discontinuity in the function over this given interval. All right, and complex roots are not easy to search for because it's a two-dimensional thing, so here we're just only assuming one-dimensional functions or equation. So here we're not discussing the complex roots. And for special types of functions, complex roots are easy to find. For example, for polynomials, we discussed this in other tutorials, that we can apply a method called Lagrange's method, and you find all the roots, whether real roots or complex roots. All right, now for searching real roots for real functions, we can employ several methods, and the main difference is the convergence, the speed of convergence. So the criteria here is the speed of search or speed of convergence. All right, so the speed is a key, and that really depends on the behavior of the function, whether or not it's smooth, it has first derivative, the first derivative is continuous or not, etc. Now we start with the general lemma of root bracketing. So this is a term that you might hear a lot when we're talking about the finding solutions, real solutions of a real equation. Root bracketing, and in simple terms it means you take an interval. So if this is a plot of the continuous function over the given interval, we can start with some initial guess and try to bring that guess to as close as possible to the actual root. Now obviously we're talking about computer methods, numerical methods. So in computer we have limited digits of accuracy, so we can never get the exact solution unless the equation is very simple, like x minus 1 equals 0. So the solution, if the solution has analytic solutions, so if the equation has analytic solutions, then yes, we can get the exact value. But if not, then we have to start with an initial guess and try to bring it numerically as close as possible to the root, the exact value. And there are different ways to estimate the error, right? So we have some search interval, which is called the root bracket, and then we try to look into the points inside the search interval and try to make it smaller and smaller around the root until the length of the interval is so small that even the beginning or end or any point inside the interval is closer to the root than the error that we're going to tolerate. Okay, so the general lemma of root bracketing assumes only a continuous function, so the only condition on the function is continuous, but it's a very weak thing because it doesn't guarantee the existence of root. And then based on this we can develop a method called bisection method. That's the very basic method, and you just divide the interval into halves and then search in each half until you get arbitrarily close to the root. And we can enhance this bisection method and have Brent's method, so that's more like an enhancement to the bisection. And then we have Newton's method or Newton-Raphson's method. So this method, Newton's method, has a kind of faster convergence than the bisection and Brent, but it has the assumption of the existence of derivative f prime of x. So if the function is smooth but its derivative is not defined over the interval, or basically f prime is discontinuous, then Newton's method is not guaranteed to work. All right. Now Newton-Raphson's method enhances the original Newton's method, and there are other methods that basically generalize all these methods, which is one of them is a generalized Taylor method, and that's based on the Taylor series, Taylor expansion of the function. And if you recall, we discussed the concept of Taylor expansion of a function, and basically Taylor expansion gives you a polynomial of some degree, and if you're expanding around a specific point, that polynomial approximates the function in a neighborhood of that point. All right, so let's start by looking at this Wikipedia page. I'm just reading the text from this page. It's called root finding algorithm. So if you go to Wikipedia and search for root finding algorithm, you can find this page. Now, to quickly go through it, it says in mathematics and computing, a root finding algorithm is an algorithm for finding roots of continuous functions. So we're dealing with continuous functions. That's the first keyword. A root of a function f from the real numbers to real numbers. So f could be real, the input is real number, the output is real number, or from the complex numbers to complex numbers. So the input, the variable could be a complex number, and the function could also return a complex number. Is a number x such that f of x equals 0. All right. Now 0 could be a real number or complex number. As generally, the roots of a function cannot be computed exactly, all right, unless we already know that the equation has analytic solution, nor expressed in closed form. Root finding algorithms provide approximations to roots, expressed either as floating point numbers or as small isolating intervals, or disks for complex roots. An interval or disk output being equivalent to an approximate output together with an error bound. Solving an equation f of x equals g of x is the same as finding the roots. So solving a general equation with expressions on both sides, it's equivalent to finding the roots of a function f of x minus g of x. This is very basic and trivial. Thus, root finding algorithms allow solving any equation defined by continuous functions, right? However, most root finding algorithms do not guarantee, so I'm going to highlight this, do not guarantee that they will find all the roots, and we will see, especially for the first method or most of the methods. For example, we look at bisection method. It just only can find one root at a time depending on the initial starting search interval. So most root finding algorithms do not guarantee that they will find all the roots. In particular, if such an algorithm does not find any root, that does not mean that no root exists. So even the algorithm fails to converge or find a root, that doesn't mean that the function doesn't have a root on that interval. Most of the time, it means that our initial guess was wrong, or our initial search interval was not correct. Okay? So in most of these algorithms, if your initial guess is not close enough to the root, you probably don't get a convergence and the algorithm fails. So you have to start with a close enough approximation and then push it towards the root and make it arbitrarily close. That's the whole idea of root finding. Most numerical root finding methods use iteration, and we will see that. For example, recursive algorithm, which is the whole point of doing bisectional search or binary search for the root, is based on recursion, producing a sequence of numbers that hopefully converge towards the root as a limit. All right? And we discussed the numeric sequences and what it means when we say that the limit of a sequence, the meaning of the limit of the sequence, and what it means to have a sequence converge to a number. They require one or more initial guesses, so we need initial guesses of the root as starting values. Then each iteration of the algorithm produces a successively more accurate approximation to the root. So we start with the initial guess, and the algorithm tries to push it based on the behavior of the function, push it as close to the root as possible. Since the iteration must be stopped at some point, these methods produce an approximation to the root, not an exact solution. Many methods compute subsequent values by evaluating an auxiliary function on the preceding values. We will see this, for example, generalized Taylor method, or if you look at polynomials, the Laguerre method. They usually involve an auxiliary function. The limit is thus a fixed point of the auxiliary function, which is chosen for having the roots of the original equation as fixed points and for converging rapidly to these fixed points. All right, so let's just try to understand visually what it means for a function f of x to have roots, right? So if this is the vertical axis, which is the values of the function, and this is the horizontal axis for x, for the variable, and if the function crosses the horizontal axis, we say that it has a root at that point where the function crosses, right? Because that's where the vertical axis is 0, all right? And let's call the value of the root r. So if f crosses the horizontal axis at point r, it means f of r is 0. But then it could, in the neighborhood of the root, the function could be increasing, monotonically increasing or decreasing. So f prime could be positive or negative for all the points in the neighborhood of the root. And the concavity could remain the same. So f prime of the f double prime, the value of the second derivative, could be positive or negative for all the points around that root, right? So it's either just crossing, going from bottom to top or top to bottom, and we call this a simple root. So simple root is that the function has a increasing or decreasing behavior, and then the concavity doesn't change also. So f double prime is positive or negative. An even root, or a root that has an even multiplicity, so it has something like this. So f of x is basically tangent to the horizontal axis. It doesn't actually cross. And that's a very important thing when we're developing algorithms, because most of the algorithm, especially the general lemma, depends on the fact that the sign of the function changes when it crosses the horizontal axis. But for a case like this, when we have the function actually tangent to the horizontal axis, there's a zero here, but f prime becomes 0 and f double prime doesn't change sign, so the concavity becomes stays the same, so always the function is curved upward, right, for all the points around the root. By the way, this green arrow is the local tangent line on the function at the root. So here the tangent line is horizontal, which means f prime is 0, right? Now we see the function could be tangent from the up or bottom, so from top or bottom, which is the third case. And this is also an even root. So the function actually doesn't cross the horizontal axis, it just becomes tangent and then goes back. That means the concavity doesn't change. So f prime is 0, but f double prime it doesn't change sign. The sign stays the same in a neighborhood. So here f double prime is negative, here f double prime was positive. And this is also an even root because the function becomes tangent to the horizontal axis. X minus r squared or x minus r to the fourth power. These are the behavior of the function, or any even any x minus r to some even number, integer number. These are the behavior of the function around in a neighborhood around the root. Okay. Now on the other side, we can have odd roots. These are roots with odd multiplicity, and the condition is that f prime could be 0, so the function could become tangent to the horizontal axis, but then it actually crosses, so it becomes tangent but then crosses. And the condition here is that f prime is 0, so it becomes tangent, but then f double prime changes sign. So positive f double prime, negative f double prime. And the condition for changing sign for the f double prime is that the f double prime should actually be 0 right at the root, right where the function becomes tangent. And we call this a stationary point of inflection. Stationary point of inflection. So whenever the function changes the concavity, if it's concave and then becomes convex, we have an inflection point. And if f double prime is 0 and then it changes sign, we have a stationary point of inflection. Now f double prime is 0, but the function doesn't become tangent, so f double prime is 0 and then it changes sign, so we have an inflection point right at the root, but f prime is not 0, so the function is not tangent, so we still end up with a simple root. So the behavior of the function is still a simple root, x minus r. Alright, so if you have x minus r cubed or x minus r to the fifth power, then f prime should be 0 at the root, so which means we have a stationary point. So the only way that we don't have a stationary point is that the inflection point is non-stationary with x minus r to the first power. Okay, so what is the general lemma? F of x equals 0. Consider a continuous function f of x over the interval a and b, and a and b are not included because it's very easy to check whether or not these are actually the roots. So if the value of the function at the beginning and end of the interval changes sign, so f of a has a different sign than f of b, and remember the only condition on the f is the continuity. We're assuming that it's continuous over the entire interval. If f of a times f of b is 0, which means f has different signs at beginning at the end, then f must have at least one root. So the existence of one root is guaranteed. F could have more than one root, but it's not guaranteed that we can find them. The only thing that we can confer from this the fact that fa times fb is negative is that we must have at least one root in this interval. All right, and you can look at this case. For example, here f crosses the horizontal axis, so the root is here, and f of a is negative, f of b is positive, right? So in a neighborhood around the root, the function is increasing, and then we have one root here. Now obviously the function could go up, come down, and then go up again. It could have 2 or 3 roots, but the only thing that we can say with absolute certainty is that we at least have one root. We don't know if I have more than one root or not. All right, so the exact number of roots is not guaranteed. We don't know how many roots is not guaranteed. Only the existence of one root is guaranteed. The interval can become arbitrarily small. So if I try to push a closer and closer to the right and b to the left, then I make the interval smaller and smaller. And once the size of the interval, basically b minus a, is less than the error, I can call any point in that interval an approximation of the root. And that's the whole idea. Typically, when the size of the interval that has at least one root is less than the error that we're looking, then we take the midpoint of the interval as the approximation of the root. Okay? Now in the second case here, the second plot, f is decreasing. So f of a is positive, f of b is negative. And because we know that f is a continuous function in this interval, it is guaranteed to cross the horizontal axis at least one time, because there is no way that it can have a negative value at the end, but it's not crossing the horizontal axis at least once. So if it goes down at some point, then comes back up, it always remains positive. The only way for a continuous function to change sign, at the beginning it's positive and the end is negative, is that it should cross the horizontal axis, which means it should have a real root, at least a real root. Now one of the things that we can immediately confer is that if f of a is positive, for example here or here, but then f prime is greater than or equal to 0 for all x, for all the points in this interval, which means the function is increasing. So if f of a is positive and the function is increasing over the interval, it can never go down, because as soon as it goes down, f prime becomes negative, which is in opposite to our assumption, right? It's contrary to our assumption. So if f of a is positive and the f prime is also positive over the interval, then the function can never go down, so it can never cross the horizontal axis, so it doesn't have any roots, right? So this is one test that we can do to see whether or not the function has roots or not. Now obviously the other case is that if f of a is negative and the f prime is also negative, so the function starts from a and it has to go down, it cannot go up, because going up means f prime is positive. So if f of a is negative and f prime is also negative, the function has to go down and it can never cross the horizontal axis, so it doesn't have any roots. All right, so what is a bisection method? So bisection method is a combination of bracketing of the root and a binary search. All right, so again, let's do a quick review. If we have a simple root, we know that the function is guaranteed to cross and change sign, right, when it crosses the horizontal axis. So if I start with an interval and see that f of a, f of b is negative, then I know that my function is crossing the horizontal axis. Similarly, for an odd root, we know that even if we have an inflection point and the function is tangent, if it has an odd root, it means that it's getting tangent, but it changes the concavity and crosses the horizontal axis. So again, the f of x changes sign, so we can use the general lemma and try to search for that root, right? But the problem is that if we have even root, when the function just becomes tangent, the problem here is that it doesn't cross the horizontal axis, so the sign of the function doesn't change. So it doesn't matter how small the interval is, f of a times f of b is always positive here. Therefore, I don't know actually if I have a root or not. So using the general lemma for the cases that we have the function tangent to the horizontal axis is not useful. We cannot do a search and find the root. All right. This was the initial introduction to the root finding. In the next video, I'll continue with the bisection method and try to implement it in Java. Thank you for watching, and I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial, I'm going to continue our discussion on root finding algorithms and bisection method. So this is the first method that we're going to discuss, and we said that bisection method doesn't really work for the cases where the function is actually tangent to the horizontal line and it doesn't cross the horizontal line. And the problem with that is that in the bisection method, we try to bracket the root, which means we try to start with an interval around the root and look at the basically the sign of the function at the beginning and the end, and try to reduce the size of the function until we get very close to the function. And it all is based on the sign of the function. So if the function doesn't crosses the horizontal axis, it doesn't change sign, and our bisection method actually fails. Alright, so fast and effective for simple or odd roots, because in these cases the function actually crosses and changes sign. And its order, it's a binary search, or the order is the log. So it's not linear or exponential, and it's a log, so the growth is log. And it's based on a binary search, and I'll explain what it is. And it's the simplest method based on our general lemma, which says that if f of a times f of b is negative, we are guaranteed to have at least one root. And it does not work for roots with even multiplicity, where the behavior of the function is tangent on the horizontal axis. All right. Now, how does it work? So with the root bracketing, we start with an interval that we know that the function has at least one root, and based on that is based on f of a times f of b is less than or equal to 0. Now, as I mentioned before, equality here is not necessary, because I mean it's trivial that we should check for a and b first to make sure that whether or not they are the actual roots. So it's very easy and trivial. So we can assume that they are not the roots, because if they were, we assume that we have already tested them and we have found them. But let's, for the sake of argument, let's have the equality here. All right. And so if f of a times f of b is negative, which means that, okay, our continuous function has in fact a root. And the way the bisection method says that, okay, now divide the interval in half. So look at the C0, which is the midpoint, a plus b over 2. And start the same. Now look at the interval a C0 and C0b. All right. If f of a times f C0 is less than 0, we know that the root, if we have only one root, it should be here. We could have more than one root, and the other root could be in the other half interval. Well, at least we know that if f of a times f C0 is negative, we are guaranteed that we have one root in this interval. Okay. Then we again find the midpoint here, C1, which is a plus C0 over 2, and then test the f of a times fc1, and then fc1 times fc0, and then also for the other interval. So one path is like this way, we divide in half and continue, or if f of a times fc0 is not 0, it's actually positive, then and fb times fc0 is negative, then it means that the root is actually in this half of the interval, in the second half. And then we find the midpoint c1, which is b plus c0 over 2, and then test for the other two halves, c0 c1 and c1b. All right, now the beauty here is that we can do it recursively. We can employ a recursion. We start with an interval and we try to recursively go down the tree to find the solution. And when do we stop? If you recall, when we discussed the recursion for the sequences, we said that we should have initial conditions or the stop condition for the search. And the initial condition is that when the interval that we end up with, like the length of the interval is less than the error that we want, then we can call any point in that interval an approximation of the solution. And the typical thing to do is take the midpoint, the middle of that interval, as the final approximation. Now, what if we search and we don't find any roots? Let's say initially we don't know, we just arbitrarily pick a and b, and we don't know whether fa times fb is negative or not. So we can do two things. One, we can return null, which is not recommended. If you recall, at some point I discussed this. Or we can return nan, and nan in the double class. For the wrapper double dot nan, if you recall, we can use the nan from the double class, which is not a number. And the reason that I don't recommend returning null, because during the runtime you could actually end up with an exception, null pointer exception, which is not good because it can actually break your program. But if you end up with nan, it's not an exception, so it doesn't break your program. Alright, so the idea here is that we do recursion by doing this binary search. And then regarding the error, we can define an absolute error, and the absolute error is basically the fact that the length of the interval is the absolute error, right? Is the maximum error that we can have, because we can select any point here because we know that we have a root in this interval. And the worst case is that the root is very close to A and we pick a point very close to B as an approximation, right? So as we divide the interval in half, the error is actually also divided by half. The error is reduced. So how many steps do we need? How many times do we need to break? So that depends on our error. What is the error that we want? So again, just like the sequences, we don't know the exact value of the solution, so we don't have the exact approximation of the error. But we can define a sequence of errors. So this is actually a sequence of errors, similar to the way we define the sequence for the limit of a sequence. Relative error is the new approximation minus the old approximation divided by the old approximation, or the new approximation. Now if we start with the initial error, epsilon 0, which is b minus a, that's the initial maximum or the worst case error. And then after n division, we end up with b minus a over 2 to the nth power. That's the error for the nth step. And therefore, if we set the epsilon n to some error epsilon that we want, the number of steps is log 2 of b minus a divided by the epsilon. All right? Now the problem here is that, and the reason that we have other methods to enhance bisection is that sometimes the root could actually be very close to one of the A or B. It doesn't have to be right in the center or close to the center. If it's close to one of the edges or beginning or end, then doing the bisection just adds extra cost to the search, right? Because instead of dividing by 2, if we divide by 3, then we can get faster to the root. So division by 3, 4, 5 could be enhancements to the bisection method, right? And the other thing is that we can actually set an initial guess for the root. That could in fact help with the speed of convergence. Another thing that is interesting is that here, as you can see, the number of steps for a given error that we want, the number of steps depends on the actual length of the interval, right? Which is not good. So if the initial interval is large, then we have to go more and more steps. But one trick that we can do is that we can easily find a linear map that maps the value of a and b to the interval 0 and 1. It's very easy to find the function, right? And once we do that, we can also use that map to scale the function. So we find the root of the scaled function in 0 and 1, and then we scale it back. The good thing here is that the length of the function is 1. So the number of steps that we need to search in order to get the error that we want is always fixed. It doesn't change with the length of the interval, and that's a very good thing to have. All right. So you map the interval to 0 and 1, you scale the function also, and then you search for 0 and 1. Once you find the root here, you map it back to the interval a and b, to the original interval. So the way we're going to implement this in Java is we're going to implement a binary search using recursion. And step 1 is to, obviously we're looking for we have a real function, so we define a functional interface. That gives freedom and flexibility. And then actually I had it down there. So we're going to define an interface for our real function, and it's going to only have one method that has the value of the function, so it's a functional interface. And then define a class for implementing the root finding algorithms. One of the methods is bisection, and the bisection basically takes an initial value for the interval, basically takes 2 points a and b and tries to implement the bisection. And we're looking only for one root, obviously, because bisection can only guarantee one root. And then we can also make it more advanced by having an initial guess for the root. And then we have to also define the stop criteria. All right, so let's head to Eclipse and try to implement the root finding. So I'm going to create a new Java project. I'm going to call it demo roots. All right, and here the first thing I'm going to create in the source folder is an interface. I call it real root function. So this is a function that is going inside the real root object. All right, it's not necessary, but I'm going to annotate it as a functional interface. So at runtime, it's going to double check whether or not it has only one abstract method, double value, double x. So it should have only one abstract method. So if I add another method, for example, double func, it's going to complain because it says that the annotation is functional interface. And now you have 2 abstract methods, so it's not a functional interface. And the beauty of the functional interface is that we can use it as lambda expression. Which is helpful when you have a expression for the function. So this is our interface, and it's always recommended to program to interfaces, especially functional interfaces. So we're going to have a class called real root. All right. In this real root, what I'm going to have is a real root function. I call it func, and then I'm going to have a constructor real root, and here I'm just going to pass the function real root function func, and then because the name of the local variable is exactly the same, we have to use the this pointer, this.func equals func, otherwise we're shadowing the global variable in the object. All right, so the first method is bisection method. So public double bisection. As I mentioned, we get double start, double end. So this is the start and end of the interval. So what are we going to do? So obviously, if there is no root, we're going to return none. So let's start with a double root equals double dot none. All right, and then return root. So we're going to get the root, and then if other lines that we put here fail, then we just return the none. Then we're going to check for start and end points, because if you recall, I mentioned it's very easy to check for that. So if check for, and then the stop criteria, stop condition. If math.abs of func.value at start is less than the error, so we're going to define two errors: absolute error, that's 1e negative 10, and then double relative error 1e minus 15, for example. If func value at the start point is less than absolute error, all right, then what we can say is that, okay, the start point is a root, right? So return start. Else, if basically the same thing for the end point, less than absolute error, return end. All right, else if, so we have two stop condition, and then the last one is the interval is very small, so the length of the interval is actually less than the error. So if math.abs end minus start divided by end, okay, is less than real error, or let's also define it with the start. Then we're going to call it we're going to do a print stopped, and then we're going to return any point. So in order to do that, we define a variable guess, which is the midpoint of the interval, start plus end, and we just return guess. So at the sum step during the recursion, if our guess or the midpoint satisfies, if the interval satisfies basically the relative error, then we just stop and call the midpoint of the interval an approximation. So at each step, we check for the beginning of the interval, end of the interval, using the absolute error, and then we use the relative error. We could also just check for the absolute error, but here I'm just writing the actually we can add it as an or. Else math.abs end minus start is less than abs error, or math.abs, yeah, that's it. So we check for two relative errors, and the reason I'm checking for two relative errors is that either start or end could be 0. So if end is 0, this division returns infinity, which is not good. Then we can check for this one, right? So these are all the stop criteria. And what is the actual search? The actual binary search. We're saying that, okay, if so we take the midpoint and test it with the start and end. So if basically func.value at start times func.value at guess is less than or equal to 0, I'm including the equality. Then I'm going to first print that I'm going to the first partition or first half. Alright, and then I'm going to return, so basically I'm not going to return, I'm going to return, call the bisection and tell it to go inside the start and guess interval. Alright, and then obviously we have an else if func value at guess times func value at end is less than 0. We're going to do a sysout of second half, and then we're going to call the bisection on the second half, so guess and end. Alright, so if this fails, if this works, then we go inside. If it fails, it goes inside. If this fails, both of them fails, then we just return none. We say that, okay, the bisection method failed. Alright, and what the other thing I'm going to do, I'm going to do a sysout on the absolute error at each step, end minus start, and then also do a do one on the relative error. And we can have two cases, so let's use this one for example. Alright, let's go and test it. So here I'm going to create another class, the test bisection, and I want to have a main method here. And in the main method, what I'm going to do first, I'm going to create my function. So step one, define function, and I'm going to use a lambda expression. I'm using lambda expression. So my function is going to be f of x is x squared minus 2. So I'm going to define a real root function f or func 0 for example equals actually let's do this, public static test1. Yeah, I'm going to move these to, and then here I invoke test1. So here I'm going to say that x goes to x times x minus 2 using lambda, and then I define a, and it's a void function, it's a void method, and then I define a real root, and then I pass in the function. Obviously I need to use the new. Alright, so far so good. And then we're going to just do system.out. Or we can say that double root or result is root dot bisection start and end. For the start I'm going to go from 0, for the end I'm going to go from 5. And then system.out.println result. Alright, so let's see what happens. So our absolute error is first 5, right? 5 minus 0, that's the first interval. The relative error is infinity because we define the relative error here with the start point, and here it's 0, so it returns infinity. And then we go into the first half. So 2.5, it says that 0 and 2.5, the value of the function changes sign, so it goes into the first half, goes into 0 and 2.5. So absolute error is 2.5. The relative error is still infinity because the start is 0. But then it goes into the second half. 0 to 2.5, it's 1.25 and 2.5. So it goes into the 1.25 and 2.5. And then goes there, second half, first half, and eventually the absolute error becomes 9.3, 10 to the negative 9. The relative error is 6.58, e to the negative 9. Now obviously here the loop terminates because of the absolute error. So if we increase this, let's say we also set it to minus 15, we end up with the absolute error of 1.11, 10 to the negative 15, and the relative error is 7.8, 10 to the negative 16. And the root that we find is 1.4142, which is very close to the square root of 2. So let's do a sysout, math dot square root of 2. 1.4142135623733095. So it's basically the exact value, right? And let's make this minus 5 to 5. Quite surprisingly, this one fails because at minus 5 and 5, both the value of the function is positive. So the bisection doesn't guarantee any root, and it doesn't know where to go, so it fails. Actually, it didn't fail. Okay, it's so. Oh, that's okay. That's because we're not comparing minus 5 to 5. We're not comparing the sign of the function here. We're comparing basically the start with the midpoint. And here the midpoint is 0, and the function actually changes sign at 0. It becomes negative. That's why it still works. And it converges to, and again, because we look into the first half of the interval first, it looks into the minus 5 to 0 and finds the negative root, minus 1.4142. Okay? And then if I change 5 to negative 5, so again, it looks into the 5 and 0 first, so it should find the positive root, yes. I mean, obviously this way of doing things is not recommended, but for now it works. And let's say we do minus 5 minus 2, for example. This should fail. So it returns a NaN because all the conditions, all the stop, and all these 2 tests, which are the basic of the binary search, fail. So eventually it returns a NaN. And that's a good thing because then we can check whether or not we have the bisection failed or not. We're not throwing an exception, or we're not returning null. We're just saying it's NaN. And it's much easier to handle NaN than, for example, an exception or a null. So if I say 2 divided by result is NaN, the result is also NaN. So it doesn't throw exception, it doesn't throw error, it just returns a NaN again. Okay, this was the idea of the bisection method and the binary search. We can, let's say, for example, the function is tangent to the horizontal axis, x minus 2 times x minus 2. And I look for 0 and 3, for example. It fails. because the function doesn't change sign. So none of these tests work actually. None of these tests results in a recursion. But if we have an odd root, so we have x minus 2 3 times, then yeah, it converges to 2 with a relative error of 10 to the negative 5. And yes, so this was the idea behind the bisection. In the next videos, we're going to look into other methods, the methods that are more advanced than just a binary search. Thank you for watching, and I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial, I'm going to continue our discussion on numerically finding roots of a real function, and we are looking for the real roots. And if you recall, we started with looking at the general lemma. So if we said that if we have a continuous function f of x and we want to find the real roots of f of x equals 0. Now continuity, we're assuming that the function is continuous over the interval that we are searching for the roots. Now it could be discontinuous over other intervals, which we don't care. But if we are looking for the roots over some interval a and b, here we're assuming that the function is continuous over this interval. And if it's continuous and the value of the function changes sign between the initial point and the end point of the interval, this lemma guarantees that there is at least one root in this interval, right? The exact number of roots is not guaranteed, that's for sure, but if the continuity is satisfied, then we definitely have at least one root over this interval. There is no way for a continuous function to change sign from a to b but not crossing the horizontal axis. So it has to cross the horizontal axis in order to change sign from a to b. And we said that this lemma is the fundamental, or the basis for the most fundamental root finding algorithm, which is the bisection method, and its order is log. By order I mean the number of steps, because it's at the end of the day all the root finding algorithms are iterations, or generate a sequence of real numbers that hopefully converge to the exact value of the root, right? So it's basically iterations. At each iteration, the algorithm pushes the estimation closer and closer to the root, or at least that's what we hope for. And there are some tests to see whether or not this iteration or the sequence of the approximations are actually converging or not. All right? And we said that the bisection is a very fundamental method, and it's the simplest method, which means from the function f of x, the only information that you need to calculate is just the values of the function at some points, right? And the basic idea was that break the interval in halves, and in each half apply the general lemma. Okay, if we know that we have a root, then one of these paths should converge the root. If we do not have roots, the algorithm should return a nan, not a number, right? And we said that in Java we use the double dot nan from the double. And it's better to return nan instead of returning a null value, okay? And the only problem with bisection is when the function is actually tangent. So we have a tangent root, and we said that this means that the behavior of the function is some even. If you use the Taylor expansion of the function around this root, the behavior is x minus root squared, or the power of 4 to power of 6, or any even power of x minus r. That's how the function behaves. That's basically the format of the Taylor series around this root, okay? And and we also talked about the error, and we said that if you look at the sequence of the approximations for the root, and we define the relative error of the convergence or the absolute error, then the relative error depends on the size of the initial interval b minus a, and because at each step we're dividing the interval by half, the worst case error also is reduced by half, because the worst case of error, at some point we have to call it the convergence, which means at some point we end up with a small interval, and the worst case, and we have to pick a point in that interval and call it the approximation of the root. And we said that the best case is, the best thing to do is just pick the mid value of that interval. So the worst case eventually becomes the length of the final interval, and the error, the worst case error, is also reduced by a factor of 2 each time. So the number of steps that we actually need to get the error that we want is log 2. And then we said that we can make it we can go one step further, and instead of starting with the midpoint, because there are cases that the root might be closer to one edge of the initial interval, right? And we might have an idea of the approximation of the root. So we can also include an initial guess for the root. So we put the initial guess, and then we do the bisection on those two intervals instead of the midpoint. Okay, so that's one way that we can make a little bit of improvement. And in Java, we said that almost all these root finding algorithms are kind of recursive. So we use recursion, which is a very powerful tool for implementing these root finding algorithms. We defined the function, the real function, we defined it as an interface, so it automatically enforces the function to be real. And then it's a functional interface, so we can easily use lambda expressions. And then we created a class for finding roots, and we implemented the bisection method. The initial interval, we did not implement initial guess yet, but we will do it later. And we did the binary search using recursion. And we also set up the stop criteria based on the absolute error and the relative error. Now, the idea is that, okay, let's say bisection can give us at least one root, but what if we are interested in finding all the roots? Now, the very simple thing to do is, if we are interested in finding all the roots over the interval a and b, let's just initially break the interval into smaller sub-intervals. Let's say 100 sub-intervals, all right? So, I mean, we are most likely going to hit all the roots if we run the bisection on all these sub-intervals, okay? So, the advantage here is that bisection was very simple, and it required the least amount of calculations, right? Because we only have to calculate the value of the function. We don't care about the derivative, the second derivative, or whatever, which some other root finding algorithms actually need to calculate the derivatives, which adds more cost of computation. But because bisection is pretty much fast and requires minimum calculations compared to other methods, then we can run it over a lot of sub-intervals, right? The only problem is that, okay, the bisection doesn't actually work for the tangent roots when the function is tangent, but for now, let's disregard that case. We can patch it with some other methods, or we can patch the bisection with other conditions, or use other root finding algorithms in conjunction with the bisection. But for now, let's assume that none of the roots are tangent roots. So what we're going to do is that in the step 1, we're going to break the initial interval into smaller sub-intervals, 10, 20, 100. Doesn't add more overhead, because bisection in general is pretty fast. And then we run the bisection over all these intervals, and if you recall, if the bisection converges to the root, it returns a double value, the root. If it doesn't converge, if you recall, we implemented the NaN, so it results in NaN, or it returns a NaN, which is Here it's an advantage of returning nan. Then we can check whether or not, if the root is, if the bisection returns nan, means there is no root in this interval. Okay, we might run into duplicate roots. We can also check for that. So the best thing to do is that to create a list, a data structure. If you're not familiar with the collections framework in Java, I suggest you look into that. So we are using collection framework. Okay, so we're using collection framework in Java to keep track of the roots and test for the nan, also test for the duplicates. So you can use an array list. So you can either use an array list or use a set interface. So I'm going to use an array list, but we can also use a array list of doubles, or you can use a set value of the set. Set automatically checks for duplicates, so it might be easier to use a set, but I'm going to use a list just for simplicity. All right, let's head to Eclipse and try to implement this. So we had this demo roots projects, and we already implemented the functional interface for a real root function, and we pass this interface to the real root. So it automatically enforces the fact that the function should be real. All right, so it returns a double value. And then in the real root, we have the real root function, and we pass it as to the constructor of the real root, and it sets the function. And we already implemented the bisection method, the stop conditions for the convergence, and then if it returns nan, we know that the bisection failed, we didn't find any roots. Otherwise, it goes either into the first half of the interval or the second half. All right, now let's create our new method. So let's say finding all the roots based on the bisection method. And public, and so instead of returning a double value, we want to return all roots. So we're going to return a list of double values and bisection, double start, double end, and we're going to add an integer parameter, and we call it sub intervals. So this is basically the user can determine how many sub intervals he or she wants. So let's import the list from the Java util package. Make sure that you import the right list object. It's from Java utils. So we're going to create a list of double. We'll call it roots. So this is plural roots, which means it contains all the roots. New array list of double. All right, and we need to import the array list too. I'm going to import it from Java util. All right, we actually don't need to put the double here. The constructor, the compiler can confer actually what's the type of this generic implementation, which is here. All right, okay, so eventually we're going to return roots. So initially all the stuff in the roots are null values, all the numbers. So what are we going to do? We're going to divide it into the number of sub intervals. So what we need here is, let's create an array, call it points. These are the endpoints of the intervals. Points, new double array of sub intervals plus 1. So if I want 2 sub interval, I have to have 3 points on the interval, the beginning, the mid, and the end. All right, and then we write a for loop, int I equals 0, I less than points dot length, I plus plus, And we need to also define the length of each interval, which is the end minus start divided by subintervals. Right? I call it dx. You can call it whatever you want. So if because the length, the number of points is sub plus 1, so then points I is start point plus I times dx, and this is going to be inclusive of start and end points, because obviously if I is 0 we already have the start at the beginning, but for the end point when I is the sub interval, we have a start plus sub interval times dx, which is end minus start divided by sub intervals. So we end up with end. So it's inclusive of the start and end points. All right. Now we have all the points. Let's run the bisection. Run the bisection on each sub interval. So we're writing a for again. For int I equals 0, I less than points dot length, or let's just go sub interval I plus plus. We're going to write some ifs. So what we want to do eventually is to have the create a double value, call it, let's say, potential root, and call the bisection method points I and points I plus 1. All right. Obviously we don't want to run into array out of bound exception, so I should go from to 0 to length of points minus 1. All right, minus 2. So the last index should be length of points minus 1, which is sub interval. So I should go from 0 to sub intervals minus 1. Then we have sub intervals minus 1 and the sub interval. Okay, that's why here I put sub intervals, which is length of points minus 1. And then what we're going to do, we're going to add this potential root to our list of roots if it passes our checks. So we have to add the checks. One is double is nan, which is potential root. So if it's not nan, so I'm going to negate it. We're going to add the roots dot add potential root. But that's not the only test. I'm going to also test for duplicates. So test for nan and duplicates. Basically what I'm going to do, I'm going to add a logical and say that not roots already contains potential root. So if it's not nan, is nan, which is negated, and roots already contains this potential root and negated. So if it doesn't already contain the potential root and it's not nan, add it to the list of roots, and then we're going to return the roots. All right. Okay, so now let's go to our test bisection method, and let's create another static method here, public static void test2. I'm going to run test2, and let's do exactly what we did. So define function, I'm using lambda expression, x times x minus 2. And then we're going to have real root, call it roots, plural, and let's just call it func, new real root, and we're going to pass the func. And then we're going to, or let's call it root finder, that's a more appropriate name, root finder. And then we're going to create a list of doubles, roots, root finder, bisection. But this time, instead of returning a double, I'm going to invoke the other one that returns a list, a start, which is let's say -5 to 10 or 3, and let's go with 100 sub intervals, and just we're going to return the roots, we're going to print line roots, and the list. Okay, we need to import the list. Make sure you import it from the Java util, and the list already overrides the toString method, so no need to worry about toString for list objects. It already puts them in a nice way. Alright, test 2, we should have 2 roots. Let's see. Oh, let's go also remove all these print lines here, stopped, half, first half, second half. Let's remove that from the bisection and let's run it again. Bingo. So we have 2 roots, minus a square root of 2 and plus a square root of 2, and it's pretty fast. Let's call it 1. So minus 1 1 1, bingo. Now what happens if it's tangent? So x squared is tangent and the root is 0. Yeah, it still can't find it, which is very interesting. It doesn't guarantee that it can find the oh, actually that's because I'm thinking that that's because it's maybe it's because the original objects, the roots are 0, so that could be one possibility. Let's write it as x minus 2 times x minus 2. If this returns 0, it means that it actually fails to find the root. No, it can actually find the root, which is very interesting. I wasn't expecting that. Now, for example, let's say we say math.sine of x, all right? And then let's go from 0 to 4 pi. Let's see how many roots we find. 0, pi, 2 pi, 3 pi, and 4 pi. So this is a very strong method for finding all the roots. Now if we have, let's see what happens if we have sine x squared. Now this function, sine of x squared, has basically a lot of oscillations, and that would cause a lot of roots, so it's interesting. So I'm going to, from 0 to pi, we have 0 1 2 3 3 roots, and let's plot the function sine of x squared and actually verify, and then verify the roots. So plotting is one way to verify the roots. And how do we plot that? If you recall, I said that in the mathlib library there is a package plot, and there is one object, MATLAB chart, which utilizes the jfree library, jfree chart. We will return to jfree chart and review it, but for now you can just use this MATLAB chart, which is a wrapper class. So MATLAB chart, fig new MATLAB chart. So we create an empty chart, and then I'm going to go to the build path and give it a dependency on the mathlib, and then we're going to import this, and then I'm going to create the array of doubles x mathutils dot len space from 0 to math.pi, let's say 10,000 steps, and then we're going to run the function over this over all these values. So if you recall, I mentioned you can use the array func, apply, and it takes the interface of real function, but it's different from this. So we're going to use the lambda expression value t, and then over the array of x. All right, so that's one of the beauties about using a functional interface. If you have another function, you can just use the lambda expression to explicitly define the interface. And then we're going to plot x and y, and then fig dot, we're going to render it to create the panel, and then fig dot run, and we're going to exit the application. All right. And what I need to do, I need to go to the run configuration because I'm using Mac, and remove this check mark. All right, this is the function. So we have a 0 at 0, which is correct, and then we have another 0 here, which is let me just increase the font size. It's about 1.77 something, and which is correct. And then we have another 0 here, at around 2.5, 2.5066, and another 0 here, 3.07, 3.0699. So as you can see, our root finding algorithm based on the bisection method is very powerful and can in fact succeed in returning all the roots. Obviously, if I increase the order of the function or use different functions, let's call this test 3. Let's say sine x times x again, so cube. Let's see what happens. Yeah, we have how many roots do we have? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 roots. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So our algorithm seems to succeed. At 0, the first root is around 1.5, 1.4659. The next one is around 1.84. And all the way to the last root, which is around 3.04, 3.046. All right, so this was our discussion on the finding all the real roots of a real function over a given interval. The condition is that the function is supposed to be continuous over that interval, and we're using the underlying very fast bisection method, which only returns one root or returns none. It fails. And then we basically, what we do, we just divide the interval into very small subintervals and run the bisection over that, and disregard the roots that are basically none, or roots that are repeating themselves. And this proves to be a very strong way of finding all the roots. Thank you for watching, and I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial, I'm going to continue the discussion on the bisection method for finding the roots, the real roots of a real function. And to recap, we said that in the basic bisection method, we take the interval a and b, which is the interval that we are looking for roots inside that, and the assumption is that the function is continuous over that interval. And then the basic binary search was to start with the midpoint, basically break the interval into two halves that have the same length, and then search for the root in each of them. And then we have two paths, and we go down the paths until we find the root, right? But then we said that this process can be accelerated, at least in the beginning, if we add an initial guess for the root, because instead of dividing the initial interval into two halves with the same length, if the roots is around here and we set the initial guess here, and so then we can divide the interval into two halves. One has a smaller length and is closer to the root, so that can accelerate the convergence to the root. It doesn't really change that much the order of the error and the number of steps, it probably changes the number of steps a little bit, reduce it, if we have a good guess for the root, good initial guess for the root. Okay, so let's head to Eclipse and try to implement this. So we have our demo roots projects, and we have the real root function, which enforces a real function with a real argument, and then we pass this to the real root object that finds the root, and we already implemented the bisection method. I'm just removing these commented parts. We already implemented the bisection method, start and end, and it already divides the interval into two halves with equal length. We have the stop conditions, and then we have the actual binary search. And if the binary search fails, we return a none, or not a number. If you recall, we also implemented a bisection which returns a list of roots, so finds all the roots, all the real roots over the interval, and based on how many times it divides the interval into subintervals, so how many initial subintervals it looks for. So what I'm going to do, I'm going to modify this bisection to add an initial guess. So let's copy this and then add the double guess, and I'm going to remove this. So that's pretty much it. Believe it or not, this works exactly what we wanted. So this is the bisection method with the initial guess. And if you probably can guess what I'm doing here. I'm using method overloading, which is a powerful technique, method overloading technique. And this method takes an additional guess, and I basically, so the stop conditions are basically the same, but this guess is just half of the start plus end, right? If the length of the interval is small enough, then we just call the midpoint as the approximation. Other than that, I do the binary search, and here basically this guess is the initial guess. So if the start and initial guess is less than 0, it means the root is here, and we call the bisection, which is the other bisection method, which is this method, right? It already computes the guess as the midpoint. So the only thing that we're changing here is that addition of the initial guess causes that the initial breakdown to be uneven, right? So the initial breakdown is start to initial guess and guess to the end. It's not a midpoint. So let's go and try to test this. Test 3, public static void test 4, and I'm going to run test 4. We're going to do the same thing here as the first one. X squared minus 2, and func, let's call this func x times x, and we're searching for 0 and 3 with the initial guess of let's say 1. Okay, now the problem here is that if I put an integer here, it goes and calls this method, which takes an integer, and it returns a list, and that list is not a double value. So that's why the compiler is complaining. It's saying that I'm invoking that method, but it returns a list, the method that also takes an extra integer, but it returns a list, but I cannot convert it to a double. So you have to make sure that you're putting a double value here. So this means that run the bisection on this function over the 0 to 3 interval, but the initial guess is 1. So initially it goes into, instead of searching for 1.5 to 3, it goes and searches for 1 to 3. So in this case, it's not that, it actually a little bit less improvement, but it still works. But if I set the, let's say, I don't know, it's like 2.0, so it's a double value. So it looks for 0 to 2 and 2 to 3. And the root is 1.4, so it goes into the 0 and 2. 1.4. So if I said 1.3 or 1.5 even, then this is not different from the bisection method. So if I put 1, let's say 1.3, then one of the roots is very close to this interval. So it goes into 1.3 and 3. Alright? So this is one thing. Another thing that we can do, which is much more interesting, is that trisection method, exactly like bisection, but we can accelerate it much more. So the way we accelerate it more is, instead of dividing into 2 halves, we divide it into 3 halves, and then run the bisection, or run the recursion. So we're still doing a recursive trisection. It's a recursive method, but exactly like the bisection, but we just divide into 3 halves. And as you can see, the number of steps ends up being log 3, not log 2. So that could significantly reduce the number of iterations. And the other things are the same. So the error is basically the initial length divided by 3 to the power of n instead of 2 to the power of n. As you can see, let's say n is 4, then 3 to the 4 is 81, 2 to the 4 is 16, so 16, 80, so it's a factor of 5. So this could have huge improvement in terms of the speed. So, and it's very easy and very similar in terms of implementation. It's very similar to the so I'm going to, implementation is similar to bisection, and we're going to use recursion again. Okay, so we're going to implement it exactly like bisection using a recursion. The stop conditions are the same, but this could have much faster convergence. All right, let's go to Eclipse. In the real root object, I'm going to here copy this. After this, I'm going to create a trisection method over the interval. Right now we don't have any initial guess, doesn't matter, but then we have to divide into 3 intervals. So I'm going to create a variable called delta, which is end minus start divided by 3. Instead of 2 we have 3, and then I'm going to have 2 guesses, right? Guess 1 is start plus delta, and then guess 2 is start plus 2 delta, or end minus delta. All right, and then here, if the start value is the root, we return start. If the end value is the root, we return end. If the length of the interval is small, then we're going to return the midpoint, start plus end. Okay, and then we're going to do a ternary search instead of binary search, and we check for the start and guess 1. If it's negative, we go into a start and guess 1 and call the trisection. Otherwise, we check for guess 1 and guess 2. If it's negative, we go into guess 1 and guess 2. And finally, we check for guess 2 and end. If it's negative, we go into check guess 2 and end. And remember, these are trisection, so we do a recursion on the trisection. We could in fact do a binary search again, but let's just go trisection. Okay, if all three ternary searches are failed, then we just return a NaN. All right, let's go here and do a public static, or maybe just copy and paste this one. Test 5. I'm going to run test 5. I don't have an initial guess, and instead of calling the binary search, I'm going to call the trisection. Instead of bisection, I'm going to call, and this should be much faster. Yeah, and we can also improve this, go from 3 divisions to 4 divisions, 4 sub intervals, which makes it much faster. But as you can see, even the dividing into 3 becomes a much faster algorithm. Okay, and similarly we can modify the bisection that returns all the roots and do a trisection that returns all the roots, and we have these. Instead of calling the bisection, we call trisection, and that's it. So you see, the beauty of improving this and writing recursively is that everything is the same, you just change the name. Alright, so I'm going to use this one, but call it test 6. And in test 6, I'm going to call the trisection method. And let's run this. As you can see, we again have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 roots, and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, and let's double check the root. 0, 146, 184, 211, 234. So we have 10 roots, 2, 4, 6, 2, 4, 6, 8, 9, 10 roots, and this also returns 10 roots. But compared to the bisection, the trisection is much faster. Okay. Alright, so let's go back to our PowerPoints and do a recap, a quick recap. Again, so far what we have looked at in terms of the root finding algorithms were the ones that were based on the general lemma, and they only involved finding the value of the function, and no other information was checked or required. But after this, we're going to look at the methods that actually take advantage of the more information that the function has. What do I mean by that? I mean the slope of the function, the tangent lines. For example, Newton's method is a method that also looks at the tangent line. It takes advantage of that, and it could in fact be faster, provide a faster convergence. And that goes into the category of general gradient methods, even for optimization. It's not just for the roots, also for optimization. Using the slope of the function could provide faster methods, but the reliability may not be as good as the bisection or trisection. What I mean by that is you have to check for more things. In fact, you have to also check for the slope of the derivative of the function, because if it's 0, if the derivative is 0, then you're in the, for example, in Newton's method that we will look at some point, you will stuck and the algorithm fails. So having taken advantage of more information in the function is useful in terms of faster convergence, but we need to add more and more check conditions to make sure that the algorithm is working and is not going into a death loop or fails quickly. So we have to check for more conditions. But so far we've looked into the trisection, which is a much more improvement over bisection, the number of iterations, and also finding all the roots based on the bisection or trisection, which provides a very convenient way of looking at all the roots. And we will look at other methods and try to add more codes for those methods too. Thank you for watching, and I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial I'm going to continue the discussion on root finding algorithms. So far we looked into algorithms based on just bracketing the roots and looking at the sign of the function at the two endpoints. But now we're going one step further and look at the methods that take advantage of the other informations that the function can provide. So one of the methods is Brent's method, and this is I took this part from Wikipedia. And in Wikipedia, if you just search for Brent's method, it takes you to this page, and what you read is something like this. In numerical analysis, Brent's method is a root finding algorithm combining the bisection method, the secant method, and inverse quadratic interpolation. So far we've seen bisection. We will look at the secant method and then the inverse quadratic interpolation. It has the reliability of bisection, but it can be as quick as some of the less reliable methods. The algorithm tries to use the potentially fast converging secant method or inverse quadratic interpolation if possible, but it falls back to the more robust bisection method if necessary. Now this means that you check the conditions of the function, and if you cannot apply the quadratic interpolation or the secant, you just go and do the bisection. Brent's method is due to Richard Brent and builds on an earlier algorithm by Theodorus Decker. Consequently, the method is also known as the Brent-Decker method. So I've seen some softwares like MATLAB, you might see Decker method instead of Brent method, so that's another name, Brent Decker or Brent Decker method. Now before we go into Brent method, let's first check out the secant method. Now here I plot a function f of x, and let's assume that we start with an initial interval which brackets the root. Bracketing means we already know that the root has to be in this interval, or the function has at least one root in this interval. And the way we check for that is just by making sure the function actually changes sign when it goes from the beginning of the interval to the end of the interval. Okay. And so this is the secant method that we're trying to look at first, and then we're going to search for the roots, let's say in the initial interval of x0, x1. This is also called a quasi-Newton method, and I'll explain later why this is called the quasi-Newton method. Now, as you probably guess, just like the bisection or trisection, we are going to implement a recursion for this algorithm for secant method. And the algorithm is like this. So we start with the 2 points that bracket the root, and then find the value of the function at these points and draw a line from the beginning to the end, and then find the point that this line crosses the horizontal axis, and most likely this point, as is shown here, is closer to the root than the original points. Okay, and then we take the x1 here and x2, which is the crossing point, and then do the same method. So from x1 to x2 we draw the line and continue to find where it crosses the horizontal axis, and then we repeat that for x2 and x3. So x3 here, x2, draw a line, and then see where it crosses the horizontal axis. And this sequence hopefully converges to the root. And in most cases, the convergence is faster than the bisection or trisection method. So in terms of recursion, let's say instead of having the x0, x1, we have the last two terms, last two approximations, xn minus 2 and xn minus 1. And then the values here are f of xn minus 2, the value of the function, and here is f of xn minus 1. Okay, so the slope of this line is f. So actually here I have the equation for this line. The slope is f xn minus 1 minus f x minus n minus 2 divided by xn minus 1 minus xn minus 2. So this is the line, okay, the slope. And then the line crosses xn minus 1 and f of xn minus 1. So using the slope and this one point, we can find the equation. And now if I want to find xn, I set the y to 0 and solve for x, because that's the point where this line crosses the horizontal axis. Okay, so x becomes xn minus 1. We take it to the other side, minus xn minus 1 minus xn minus 2 divided by the values of the function. All right, so this is the secant method, and definitely we're going to use recursion to implement it. Let's head to Eclipse and implement the secant method. So in our demo root project, in the real root, we have bisection. Let's copy the bisection here. And bisection with initial guess. We have bisection that returns a list of roots. We have trisection. We have a trisection that returns a list of roots. And now we're going to implement the secant. And we only need 2 points, start and end. And let's remove the initial guess, and the stop condition is that start plus n half. So either a start of the interval after some iteration is the root, or end, or the length of the interval is very small, so we take the midpoint of the interval as the approximation. And now we're going to implement secant method, and the way we're going to implement is like this. So I'm going to call it x1, which is the start point, and y1, which is func.value at x1. Okay, and then double x2 and y2 is func.value at x2, and double x3. Eventually x3 is x2 minus y2 times the coefficient, and this coefficient was inverse of the slope. Coef is x2 minus x1 divided by y2 minus y1. So I'm going to comment it. Coef here is the inverse of the slope of the secant line. Okay, coef. So x3, and then we're going to set the root to basically secant. Now the recursion. So how do we do the recursion? We assign the root to secant of x2 and x3. Okay, so x1, x2 is the original start point, and then we find the new crossing point from the horizontal axis, x3, and then we go into x2, x3, and hopefully this converges. Let's go and test it. We're going to here, test, and public is, let's just copy the first one. We're going to do test 7, and x times x squared minus 2. We have the function. We're going to search for the root using the secant method, and let's say -2 to 5, and the actual root is plus minus a square root of 2. So let's see. So it returns minus a square root of 2. If I set it to 0, it returns plus a square root of 2. And it's relatively fast. In order to see how fast it is, let's see how many, let's look at the steps. So I just do a system out print line on the x3, okay? And then let's just remove this one. All right, 1 2 3 4 5 6 7 8 9 10. Basically 10 steps it converges. So it starts from 0.4 and then 0.74 and then 2, 1.267, 1.387, 1.415, 414, and it basically converges. So the convergence is relatively fast. Let's return this one. Okay. Yes, this was the secant method, and we can implement exactly the same thing that we did here for the secant to return a list of all roots, trisection, secant, sub-intervals, everything is exactly the same, and we're going to invoke the secant method here. And again, this way of implementing the recursion makes life much easier when we're trying to adapt this method to any type of algorithm. So I'm going to have test 8 here. Func here, let's call this root finder, and then a list of whatever roots. It should be double, but we can also use a wildcard. I'm going to use a wildcard, which is actually not recommended, but let's use it. Roots equals root finder secant start minus 10, 10, 100 intervals, and it prints the root. We're going to invoke test. So this should be test 8, and let's invoke test 8. As you can see, there are some duplicates that happen, and that's because of the accuracy of the double. So these are all minus square root of 2 square root of, but with different accuracies. So instead of using the root contains, math.abs of let's change it to the potential root. So we know that the potential root, we can add another if to check the accuracy. So basically we should check this one with all the roots inside, and if the difference is less than the absolute error, we should assume that it's the same. And right now the accuracy here is not exactly the same, but these numbers are pretty much the same numerically. That's why it returns more roots than we actually have. So what we can do is that if it's not nan, we're going to check another maybe have a boolean here, repeated is false, and then for int I equals maybe j equals 0, j less than roots dot size j plus plus, if math.abs potential root minus roots get j is less than absolute error, then repeated is true, and then if not repeated, add the root to the... Okay, now it works. So we're using secant method over some interval, let's say minus 2 to 10, for example. This should return only 2 roots, okay? Minus 1 to 10, this should return 2 roots, 0 and 10. This returns only 1 root. Minus 5, for example, returns 2 roots. All right, so this is the secant method. And now if we head back to the Eclipse and go to actually to see what the Brent method is. Now Brent method is exactly similar to the secant method, but instead of having a linear interpolation fitting a line, we do a quadratic interpolation. So a second degree polynomial instead of a first degree polynomial. But in order to do a second degree polynomial interpolation, we need an extra point, right? We need 3 points to fit a second degree polynomial or a quadratic polynomial, okay? So the assumption is that the root has been already bracketed, which means we already know that in the interval of x1, x2, we definitely have at least 1 root. And then we start with an initial guess, x3, and then use these points x1, x2, x3. Use the y values. So y1 is f of x1, y2 is f of x2, and y3 is f of x3. And we do a quadratic interpolation. And this format of quadratic interpolation is very easy to remember, and that's called the Lagrange interpolating polynomial. So basically the idea here is that you take y1, y2, y3, and the polynomial, it should return the value x1 when you substitute y with y1. It should return x2 when you substitute y with y2. And in order to do that, we have x1, x2, x3 with some coefficients. And the coefficients are, for example, for x1, the coefficient is the 2 other indices, y minus y2, y minus y3, y1 minus y2, y1 minus y3. Okay, so here I, j, k run from 1, 2 to 3, and I and j and k are different. So we have 3 combinations of pairs, right? 1, 2, 1, 3, and 2, 3 for I and j. And then k is also the 3rd index. So for example, the coefficients of x2 is y minus y1, y minus y3, y2 minus y1, y2 minus y3, okay? So we do this quadratic interpolation of these 3 points for the y values, and then exactly like the secant method, we find where it crosses the horizontal axis, and hopefully it's closer to the root than the previous points. So if we set y to 0 here, you get yi, yj, yk minus yi, yk minus yj times xk, okay? And we had x1, x2, x3, and then this one is the new point, x4, and then we do the recursion with x2, x3, and x4, okay? So this is the idea, and obviously you can see that we can increase the order more and more. So instead of quadratic, we can start with 4 points and do a 3rd order polynomial, but there's really no need for that. So let's head to Eclipse and try to implement Brent's method. Let's go to real root. So I'm going to copy the secant method here and change it to Brent. And for Brent, basically we need the initial guess 2, and then the stop condition is still the same. If after some iterations the interval is small, so if the start point is the root, we return it. If the end point is the root, we return it. If the length of the interval is very small, then we return the midpoint. Now implementing Brent's method. Okay, exactly the same thing. X1 is start, and then Y1 is func at X1, X2 is end, Y2 is func at value X2, X3 is guess, and Y3 is func at guess. Okay, and then eventually we want to have X4, which is coef1 times X1 plus coef, these are the interpolation coefficients, X2 plus coef3 times X3 after replacing the y with 0. So coef1 is the coefficient of X1, so we should use Y2, Y3. So Y2 times Y3 divided by Y1 minus Y2 times Y1 minus Y3. And then double coef2, we should use Y1 and Y3. Y1 times Y3, Y2 minus Y1, Y2 minus Y3. And then double coef3, we should use Y1 and Y2. Y1 times Y2 divided by Y3 minus Y1, Y3 minus Y2. Okay, and we find X4, and then we run the Brent for the recursion. We run Brent on X2, X3 and X4, and in order to check the convergence, I just do a sysout on the X4. Okay, then X4 is the new crossing point. Crossing point with the horizontal axis. This is where y equals 0, the polynomial, the interpolation. All right, let's go to the test. Let's copy this. Test 9. I'm going to run test 9, and then we're going to call the Brent on the 0 to 5 with the initial guess of 1, for example. And let's first comment this. So 1, 2, 3, 4, 5, 6, 7. See, after 4 steps, it already has a 3 or 4 digits, 3 digits convergence, 3 decimal point accuracy. So it's pretty fast. If you recall, secant you required I believe 10 steps. Okay, I removed the print value of the secant method. Okay, let's comment this. And test 9. So Brent is relatively faster than secant, but we didn't check for one specific condition. If any of these fails, y1 equals y2 or y1 equals y3 or y2 equals y3, then these numbers are not a real number, it becomes infinity. So we have to check for that. And to see that, let's say here x squared minus 2 is an even function. So if I put minus 5 to 5, right at the first step, it fails because it cannot calculate the coefficients. So it should return a nan. Yes. So we run into error because it cannot converge because it returns a nan. But if I change it to anything else, it should be fine. Yes. All right. You just have to be careful for that, and that's why in the in the Wikipedia, if you recall, it says that the algorithm tries to use the potentially fast converging secant method or inverse quadratic interpolation if possible, but it falls back to the more robust bisection method if necessary. So if somehow the quadratic interpolation fails, we can program it to fall back to the secant method, and if the secant fails, we can program it to fall back to bisection method. Obviously, I didn't do it here in the code. I just directly implemented the Brent's method. But you can, as a practice or as an exercise, you can try to check these coefficients and try to fall back. For example, let's see what happens if we divide by 2 over 0, for example, a double 0, infinity. So it either returns infinity or a nan, not a number. And we can check for that, and if it fails, we can fall back to the secant. Now, obviously, I can also have a method for the Brent that returns a list of roots with the subintervals, but first I'm going to also create a method for Brent that doesn't have an initial guess. And you can probably guess how I'm going to do that. I'm using the method overloading. So in the first step, we just manually define a guess, start plus end, the midpoint, and then we call the previous Brent method. Okay, so this just assumes that the initial guess is the midpoint in the middle of the interval and everything is the same. And then we have the Brent. Instead of secant, I call the Brent and use this method that only takes 2 points without initial guess. And this shouldn't be integer now, this should be a double. And in order to check for that, I'm going to use this. This is test 10. And again, I'm using the wildcard here and call the Brent method with an integer, and we're going to invoke test 10 minus square root of 2 square root of 2. And let's say we have x times math.sine of x. We have a lot of roots. But the problem is that some of them are duplicates. Let's see. 2.76 e minus 8, 1.95 e minus 8. These are all 0. And that's why it's failing to recognize that. So maybe instead of having this absolute error, when it goes to 0, let's say e minus, I don't know, 7 or something like that. Nine, 6, 12, minus 9, 15. And we can also check by just plotting the function. And as you can see, from minus 5 to 10. From minus 5 to 10. We have one at 0. We have here. And so the problem here is that there are some roots that are outside 15 minus 9, 12, 6. One, two, three, four, 5. So there's definitely some problem here. 34. We can also maybe plot minus 50 to 50 because there are some roots apparently outside the interval. And then let's look at the 43. So there is one root here, 4398, so it's 44, so that's correct. And there is one root at 2 here, 2.18. Okay, no, 2.18 e minus 8. So this is basically 0, which is correct. We have a root at 0. And then minus 6.28, which is minus 2 pi, and that's 0. Minus 3.14, it's minus pi, it's 0. Plus pi, minus 34. So minus 34. 0.55. 34.55, yes. So the roots are correct. The problem here is that they are not all of them are in the interval that we want them to be, and that's very bad. And that's because of the way the secant works. So for example, if I, instead of the Brent, I call trisection, I get 1, 2, 3, 4, 5. Exactly 1, 2, 3, 4, 5. So I'll leave it as a homework to you to try to modify the code for the Brent method, the one that returns all the roots, to make sure that only the roots that are in the interval are returned. And that's very easy, right? So you check for these, and all right, let's just add it. You don't need to practice on this, so I can do it for you. And then basically start is less than or equal to the potential root, and the potential root is less than or equal to end. Now if I call the Brent again, which returns a list, hopefully this time we end up with yes, 2 pi. Okay, there is one that is 9.42, which is here. 1, 2, 3, 4, 5 roots. So the first one, 2.8 in 10 to the negative 8, this is 0. And then minus pi, pi, and then 2 pi, and then 3 pi. So now I'm just limiting the result to the interval. But as you can see, you have to check for that, and the Brent, if without this, it actually returns other roots that are outside the interval. That's because this line could actually go farther away, and then when you do the continue the secant or the Brent with the quadratic polynomial, you can end up with the other roots if the function has more than roots, because yeah, this point could end up outside the initial interval. Alright, so far we have the bisection, trisection, secant, and Brent method, and next we're going to look at other methods such as Newton-Raphson and see how they actually work. Thank you for watching, and I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial I'm going to continue the discussion on solving equations and finding real roots of real functions. And so far we have discussed the general lemma of root bracketing, and the idea was that the sign of the function should change if it's a continuous function and the sign changes over the two ends of the interval. We are guaranteed that we at least have one root, and we call the interval basically a bracket for the root, which means that there is one root in this interval. That's the meaning of root bracketing. We looked at the bisection method and implemented it in Java. And also we extended the bisection into trisection method, where we divide the root bracket into 3 pieces instead of 2 pieces. And then we also looked at the secant method, and we looked also at the Brent's method. And there are 2 methods left. One is the Newton or Newton-Raphson's method, and the last one is the generalized Taylor method. Now, to recap, we said that the behavior of the function locally around the root could be either a tangent, where it could be either a simple behavior, which we call it a simple root, or it could be tangent without changing the concavity of the function. So f double prime remains the same on both sides in a neighborhood around the root, and we call it an even root. So the function is tangent. And finally we said that the function could in fact be tangent, but the concavity can change, or f double prime changes sign, or f double prime is basically 0, which is called the stationary point of inflection. And in this case we have an odd root, a root that is not simple, which means the first derivative is still 0, but the second derivative is also 0. So the order of the root around the Taylor expansion around the root should be 3 or 5. It cannot be 1. But if f prime is greater than 0, which means the function is not tangent at the inflection point, we have a non-stationary inflection point. And in the non-stationary inflection point, we in fact have a simple root. So the order of the Taylor expansion is 1. All right. Now regarding the bisection, it was very simple, and what we mentioned was that unfortunately bisection is always guaranteed to converge to the root, but it's not very fast. All right. But then the only case that the bisection may fail is when the function is actually tangent. We have an even root, right? Similar with the trisection method, the same thing, because the trisection and bisection are just based on a binary search or ternary search. And then we said that, okay, if we want to improve upon this, we can use the secant method. Now in the secant method, what we said was that we start with the bracket for the root x0, x1, and try to come up with a recursion that takes into account the behavior of the function. And the simplest way to do that is connect the 2 endpoints of the function at x0 and x1. And because x0, x1 is a bracket for the function, we know that the values of the f have different signs. So when we derive this line from x0 to x1, this line is guaranteed to cross the horizontal axis at some point in this interval. And this point then is guaranteed to be closer to the root than both x0 and x1. Okay, so by doing this, we can build a recursion. So we said that at some point, if the bracket of the root is xn minus 2, xn minus 1, we draw this line, find the crossing with the horizontal axis. We call it a better approximation for the root xn. and then we repeat the secant method in the xn minus 1 xn interval. Now the problem was that if you look at the secant method, the problem here specifically in this example, in this function, that when we continue with the recursion in the x minus 1 and xn, this interval is in fact not a bracket for the root, right? The root is here. So if we continue with the secant in this region, we end up with a root that is actually farther away from the root, from x2. So the distance of xn to the root is much smaller than xn plus 1 to the root, right? So this is a problem, and so far we did not address it in the code, but we try to go and address it in the code. And what we are going to do is that if we start with the bracket x0 x1 and then we want to make sure the recursion remains in this interval. So each time, in fact each step of the secant method applies to a valid bracket. That's the point, right? Because here xn minus 1 and xn is not a valid bracket, but we already know that the xn is guaranteed to be between xn minus 2 and xn minus 1. So what we're going to do, simply, before continuing with the secant, we decide where the root is. So we test xn with xn minus 1 and xn minus 2. If xn minus 2 and xn is a valid bracket for the root, we continue with this interval. If xn minus 1 and xn is a bracket for the root, we continue with this interval, right? So this way is a better improvement. Or we can say that then secant is guaranteed to converge to the root in this interval. Because if we continue with this and hit the xn plus 1 here, there might be a root around here. So this can in fact converge to this root, okay? So here, to clarify again, so instead of drawing this line from the xn minus 1 and xn, we want to change the code to draw this line from xn minus 2 to xn. And as you can visually see, it crosses the horizontal axis at a point that is much closer to the root than the previous one. So this gives a better convergence to the root that is in fact in the search interval in the original bracket. All right. So let's head to Eclipse. So what I'm going to do, I'm going to go to the real root class, and in the secant method, what I'm going to do here, and instead of just going into x2 x3, I'm look for the valid bracket. So I'm saying that if func.value x1 times func.value x3 is less than or equal to 0, I have to go into the x1 x3 instead of x2 x3. Else if func.value x3 or x2 times func.value x3 is less than or equal to 0, we're going to set the root to secant x2 x3. all right, and then we're going to return the, so we go into the recursion and then we come back and return the root. If none of them is a bracket, we just return that, okay? And then we can also check for initial bracket. So we can also add this fact that check for the initial bracket. So we want to make sure that the initial interval is a valid bracket. So if func.val start times func.val end is greater than 0, then we don't have an initial valid bracket, so we're just going to return double.nan. Okay, so we're just saying that, okay, this is not. We can throw an exception or just return NaN. Okay, now let's head to our test class and try to test it. Or maybe I'll just create a new class, test secant, and I'm going to write this public static void test1, and here I'm going to run test1. Okay, and let's go back here and try to copy from one of the secant tests, for example this one. So we use the lambda expression for the real root function, and it maps x to x squared minus 2, and I want to find the roots in 0 to 5. Now at 0 we get minus 2, at 5 we get something positive, so this is a valid bracket for the root. Okay, so let's see what happens with the secant method. So it converges quickly to 1.414213, which is the root, right? Now if I go minus 5 to 5, this is not a valid bracket, right? Because at minus 5 and at 5 the function is positive. So we end up with a NaN, all right? If I go minus 5 to 1, this is still a valid bracket, because at 1 we get minus 1, at minus 5 we get a positive number. So this should converge to minus square root of 2. And as you can see, now we are guaranteed that the secant converges to the root inside the interval. Okay, and that's now because of the fact that we search for a valid bracket when we're doing the recursion. And let's say we put it to 1, x squared minus 1, we return 1, and if I put this to 0, I should get the negative 1 root, which is correct. If I get this to I don't know, 5 and 0, 0 and 5, 0 and 2, this is still a valid bracket for this x squared minus 1, so I should get the 1 root, right? Now we also had now that we improved the secant method, we also had the function that returns all the roots in a given interval based on the number of subintervals. So let's also go and test that. Test 2, we're going to run test 2, and let's stay with x squared minus 2, and then instead of calling this that returns a double, I'm going to return a list of doubles, roots, and let's call this a root finder object, root finder times Brent, which returns number of, so we're going to start with minus 5 to 5 and 100 subintervals. So here we don't care about, let's import the list from the Java util. And then let's print the results. So what we see here is that we don't actually care about whether or not the initial interval is a valid bracket. That's the whole point, because we divide it into subintervals, and then we search that which subinterval is in fact a valid bracket. So we get minus square root of 2 and plus square root of 2. Obviously if I set it to 1000, the results will be the same, right? doesn't add more overhead because of this fact. It doesn't go and do the initial search, and because as soon as it sees that the sub interval is not a valid bracket, it discards it. Now we could do the same thing with the bisection and trisection, and we didn't add this thing. We said that okay, in the bisection just go do the recursion. If you don't find the root, then return null. And it worked based on the midpoint. But we can also enforce the fact that the initial interval must be a bracket. So let's try other functions. For example, x squared minus 1. Okay. I think 100 points is still fine. Let's try math.sine of x. It fails. Math cosine of let's call this minus 425. It still fails, and it could be due to several reasons. We have to look into what happens. Let's say x times sine of x. It succeeds in finding the roots. One of the roots is 0, one of is minus pi, the other one is pi. And let's increase the number of subintervals. The same thing. So it doesn't matter, doesn't add more overhead, because as soon as it sees that it's not a valid interval, as soon as it sees that it's not a valid interval, it just discards it. Here in the secant. Okay. Now the question is, so in the Brent we had this in the secant method, we had this test to make sure that the root is actually in the interval. And let's see what happens now if we remove that. Because of the improvement that we made, we are guaranteed that if there is a root in the bracket, we should be able to converge to it. So there is no worry about whether or not it's between the start and end. It's guaranteed to be there. Let's make sure that this happens. Minus pi, pi, and 0. Yes. And let's increase the interval, minus 12. So we get minus 3 pi, 0, minus 2 pi, pi, and minus pi. Okay, so we are guaranteed that the secant method, not Brent, secant. Sorry, I was running the wrong. Now it fails. Let's test with the. So we know that the Brent method works. So let's test with the secant. So the secant is still have some problem converging. And let's see the previous case. It works. Minus 4 from minus 4.5 to 1000, we get minus pi and pi. Now, interesting thing, it doesn't find 0. It doesn't converge to the 0 term. Maybe let's try with the. Still can't find a 0. Let's say we just have a linear function x. It finds the 0. And I'm assuming that's because the slope of the x times sine of x is maybe somehow Now we know that the function x times sine of x is an even function. So at 0, it's a tangent root. So if I use, for example, trisection, we might not see this. Yes, so in the trisection, we don't see the 0 term. If it wasn't a tangent, so we know that the trisection is guaranteed to converge if the root is there, right? So here, if I use the trisection or bisection, we don't see one of the zeros, which is exactly at 0, because the function is tangent at 0. But secant is also failing, and you can look into the reason why it's failing, but it's not revealing the 0. If I use Brent can in fact find all the roots, 0, pi, and minus pi. So Brent is the most successful root finder so far. And next we're going to look at the Newton's method, which is similar to Brent, but similar is mostly to secant, but it promises much faster convergence if in fact it can converge. So thank you for watching this tutorial. I hope you enjoyed it, and I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial I'm going to discuss one of the fastest converging methods, which is called Newton's method. It is also called Newton-Raphson's method. So this part is from Wikipedia, and this is a graphical representation of the method. So this black curve is the function, and just like other root finding algorithms that we have discussed so far, Newton's method also works based on a recursion. And each step of the recursion, it tries to come up with a function, with the number that is getting closer and closer to the actual root. Okay, now the way it works is that you start with an initial guess, and the initial guess should be close enough to the root. That's one of the main requirements. And then at that point, the Newton's method basically draws a tangent line. Now this becomes very similar to the secant method, but if you recall, in the secant method, let me just quickly go there. In the secant method, what we needed to do in the secant method was to basically have a valid bracket of the root, and then connect the two lines, the two endpoints of the bracket, and find the x-intercept, the point that it crosses the horizontal line. Now in the Newton's method, it says that, okay, instead of doing that, just take one point and draw a tangent line. Find the crossing of the horizontal axis, and then continue this recursion. And it's guaranteed to converge faster than the secant. So in fact, Newton's method has a quadratic convergence, while methods like bisection and trisection have linear convergence. And for example, secant method has a superlinear convergence, which means its convergence rate is between 1 and 2. So the golden ratio, if you search it, it's 1.5 something. But the Newton's method has a convergence rate of 2, right? So it could be very fast, but it also has a lot of problems. For example, so what I mean by the problems is that bisection and trisection are always guaranteed to the convergence to the root if the root is in fact inside the bracket, the initial bracket. But Newton's method may actually fail to converge even if the initial start point is close enough to the root. Okay, so I'm going to read this from the Wikipedia. If you just go to Wikipedia and search for Newton's method, this page pops up, and it says that in numerical analysis, Newton's method, also known as the Newton-Raphson method, named after Isaac Newton and Joseph Raphson, is a root finding algorithm. Okay, so it's a root finding algorithm which produces successively better approximations to the roots or zeros of a real valued function. So these are the key ones: real valued function and the real root. We're looking for real root. The most basic version starts with a single variable function f defined for a real variable x, the function's derivative f prime, and an initial guess x0 for a root of x. So not only we need to evaluate the function at x0, we also need to evaluate the f prime, the derivative of f at x0 or at each point. Now immediately you can see that if the f prime doesn't exist at one of the steps of the recursion, Newton's method fails. And another thing that you can immediately see when you look at the recursion equation is that f prime is in the denominator. So if f prime becomes even 0 at some point, then the recursion fails, right? But if we have the initial guess, we have the value of f, and the f prime is not 0, f prime exists and is not 0, then we can continue to the next step of the iteration. x1, which is x0 minus f over f prime, is a better approximation of the root than x0. Geometrically, x1 and y equals 0. So if you start from x0 and then x1 is the next point that the tangent line at x0 crosses the horizontal axis. x10 is the intersection of the x-axis and the tangent of the graph of f of x at x0 and f of x0. Okay, that is, the improved guess is the unique root of the linear approximation at the initial point. Very similar to the secant, right? The process is repeated as this recursion. xn minus 1, find the tangent line, the slope is f prime at x minus 1, and find the crossing with the horizontal axis, which is xn. Okay, is repeated until a sufficiently precise value is reached. This algorithm is first in the class of Householder's methods, Newton's method, succeeded by Haley's method. The method can also be extended to complex functions and to systems of equations. So Newton's method, because it's based on derivative, you can also apply it to optimization problems. Because even if you want to minimize a function which is positive over the search region, then you can try to find its zero. It doesn't have a real zero, but it can lead you to the minimum, and it could be one of the branches of the gradient descent algorithms for optimization. But for now, you can assume that Newton's method is this simple one-dimensional case that can give you a progressively better approximation of the root. All right. Now, as you see, we need to find the value of the derivative at each iteration, right? So how do we find the numeric? How can we find the derivative numerically? And for that, we need to do one of the approximation of the derivative. One is called forward estimation. So if h is a small number, f x plus h minus f of x divided by h is basically the slope of the line from x to x plus h. And if h is small enough, this ratio can approximate the f prime. And the order of the error, this O notation, order of error is basically, so I'm going to write this here, this is called order of error. Order of error is linear with h. So if I reduce h by half, the error is also reduced by half. Now, similar to the forward approximation, we can use a backward approximation. So instead of having x and x plus h, we can have x and x minus h. And again, the order of error is h. But there is a better approximation which is called center approximation. In the center approximation, we take the values, symmetric values around the x. So instead of having x, we evaluate the function at x minus h and x plus h, and the distance is 2h. So divided by 2h, and the order of error here is quadratic, which is much better than linear, right? So if you divide the h by 2, the error goes down by a factor of 4. Okay? So if I reduce h by 1 order of magnitude or divide it by 10, the error goes down by 2 orders of magnitude. And you can write these based on the Taylor expansion of f plus h and f x minus h. And based on those Taylor expansions, you can actually come up with higher degree approximations that have order of h3 or order of h4. And there is also a generalized method called Richardson's accelerated method, Richardson extrapolation, which accelerates, I believe, quadratically. So if you start from h, the next iteration, the error is order of h squared, and the other one is a order of h to the fourth, and etc. We will look at the Richardson extrapolation later in the course, but for now, let's just try to use this center approximation or one of these forward or backward approximations. Now, one thing here is that if we know the analytic function for the derivative, we should also be able to use that. So if my function is x times sine of x, I already can calculate the analytic expression for the derivative, right? So I should be able to feed my program the exact analytic function for the derivative if it's available, and we will see how to do that. For that, I'm going to use a new functional interface. So far for the root finding, we use one functional interface to basically define the function, but now we can have a new functional interface to define the derivative of the function. Okay, so now let's head to Eclipse and try to implement Newton's method. So I'm going to the real root and put it right at the end after Brent's method. So public, and it's going to return a double value for the root, double Newton, and it's just going to get a number guess, right? There is no bracketing here. So right now we just require that the guess is close enough to the root. So let's start with a double value for the root, which is double dot nan, not a number, and eventually we're going to return this root. Okay, so what we want to do first things first, we want to set the stop criteria or set the convergence criteria. And for that, I'm going to say that if math.abs of func.value at guess at this point is less than a absolute error, just return guess as the root, right? So if at some iteration step we see that the value of the function is less than the error that we want, then it's just the approximation of the root. We don't need to continue. All right. Next, we find the derivative. Find the derivative and perform recursion. So double x1 is the guess, and y1 is func value at the guess, or at x1, doesn't matter. Double coef, which is the derivative or 1 over derivative, is let's also define double h 1e negative 4, for example. And for the coef, we're going to have func.value at x1 plus h minus func.value at x1 minus h divided by 2 times h. So I'm going to use a center expression, and the order is of h squared. And then after this, double x2 is so x2 is x1 minus y1 divided by derivative or coef. And then recursion is root equals Newton of x2. Okay, and then we return the root. Now obviously this has a problem of going inside and being trapped forever. So the problem so far is being trapped forever, being trapped. Because if it goes inside, the only way that it can come out is to converge. If it cannot converge, it never comes out. So one thing that you can do, you can set a max iterations. So int max iterations, and we're going to set the max iterations and basically -1. So if it goes inside, we're going to reduce the number of iterations because one iteration has passed. So if it and then the convergence criteria is the same, but then we also have a stop criteria. If max iterations equals 0, we're going to basically print that system.out.println max iterations reached, and then just return double.nan. Okay, so this is the way we implement Newton's method, very similar to the secant. So let's go and try to implement it. Class or let's maybe go to the original test class. I'm going to create a let's say copy this one, and let's call this test 12, and we want to run test 12. And so x squared minus 2, let's start with our simple case, x squared minus 2, and we have the root finder, double root equals root finder dot Newton, initial guess is 5, max iterations is, let's say, 1000. And we're going to print the root, and then we're going to plot the function in -5 and 10. All right, let's see. Yeah, as you can see, we have two roots here, minus the square root of 2 and square root of 2, and we are converging to the root pretty fast. So if I set the initial start point at -5, we hit the -1.4142. Now let's see how let's look at the number of steps. Let's look at each step. So we're going to do a sysout on the x2, right, and see how it converges. 1, 2, 3. With three steps, we are already at -1.44. So we have 2 digits of accuracy. And then with 2, 4, 6. With 5 steps, we are almost there. So as you can see, the Newton's method, if it converges, the convergence is pretty fast. Now what if I said minus 50? Now it just increases the number of steps, but again, after a few steps, 2, 4, 6, 7, 8. At 8th step, we are almost there. So the convergence is pretty fast, all right? Now let's look at the more complex function, x times, or maybe let's keep the x squared minus 2, and let's also, just like the other methods, let's implement a method that has all the roots in the given interval. Start and subintervals, int max iterations. Or we can just we can have this and later overload it. Now we start with the list for roots, and we divide into subintervals, and we call our Newton's method on a given guess. So what is the guess? We're going to define the guess as the midpoint of each interval. Double guess equals basically this. .5 times point I plus point I plus 1, all right? And then we're going to pass in the guess and the max iteration. So basically we're looking for the, in each sub interval we set the guess as the midpoint, and then go do the max iterations and try to find the root. And we probably don't need to check whether or not the roots are inside, but it's good to have it as a test, and also check for repeating value of the roots, and then have it as the list that is going to be returned. All right, let's test. So let's create another test case, and here I'm going to list of double roots, and from the root finder I'm going to call the Newton method on the -5 to 5 sub intervals 100, max iterations 1000. Okay, so again the good thing here is that we don't need to worry about having a valid bracket. It doesn't matter. So that gives us more flexibility, but then the convergence is not very much guaranteed. That's one of the disadvantages. Alright, I need to also go and delete this. I don't want to look at the steps. We already have test 12, so test 13. Yeah, as you can see, it converges to the roots without any bracketing or anything like that. So that could give us an advantage over other methods that require bracketing. Let's make the function more complex. X cubed minus 3. It returns 1.442. Let's check the plot. It's the third root of the x cubed, which is 1.442. Okay, now let's look at the x times sine of x. As you can see, it returns max iterations reached, which means that there were some intervals that it couldn't find the root in, but we have 1 root, 2 roots, 3 roots, 4 roots, 5 roots, and it was only able to return that's because the search interval and the plot intervals are different. So let's see. So it wasn't able to find all the roots. It's finding the roots, one root 0, the other root minus pi and pi. It's not able to find the other roots. Maybe if we increase the number of sub-intervals, again it's not able to find these two roots. If we increase the number of iterations, it's still not able to find the roots. So there are ways to improve this, but this is the basic code for Newton's method, and also searching for the roots in all the intervals. Now if we instead of Newton we use, for example, Brent. Let's compare it with a Brent and see what happens. Brent. So start -5, 10, 100 sub-intervals. Let's see. Yes, so Brent is able to easily find all the roots. So Brent here has more advantage than the Newton. Thank you for watching this tutorial, and I'll see you in the next video. Hello and welcome to another tutorial. In this video I'm going to continue the discussion on Newton's method, and so in the previous lecture on Newton's method we discussed how to implement Newton's method in Java based on the recursion that starts with an initial guess. No root bracketing is needed, and that's a plus. That's definitely a plus for Newton's method, because there are two advantages of Newton's method when you compare it to bisection, secant, or Brent's method. The first one is that it doesn't need a bracket for the root. You just have to start with an initial guess. Obviously the downside is that the roots should be close enough, otherwise the Newton's method may not converge. But the other thing is that Newton's method has a quadratic convergence rate, which is better than bisection, which is linear, or secant and Brent, which is super linear. Like the convergence rate is 1.4, 1.5, around that number, not exactly 2. But for Brent things are a little bit different, because for Brent you can use different interpolating functions. If you recall, in the Brent we used a quadratic function for interpolating. Now some implementation of Brent's method may use a hyperbolic function to do the interpolation. You don't need to just use a quadratic polynomial. Quadratic function to x, quadratic, let's rather say quadratic polynomial. Okay, but the advantage of Newton's method, you just need to have one root. If you recall, we said that there is no need for bracketing, but if you want to find all the roots, you can divide it into sub-intervals, and the roots may in fact fall into some of the sub-intervals, so they are already bracketed. And then we apply the Newton's method in each bracket or in each sub-interval, and then we have to figure out a good convergence condition for the Newton's method in each sub-interval. Okay, and as I mentioned, even if fa times fb is positive, which means the interval of a and b may not be a valid bracket for the root, and that causes the bisection, trisection, or the secant method to potentially fail, Newton's method may very well converge the root, right? Let's head to Eclipse and look at the Newton's method that we wrote in the previous lecture. And in that case, in that lecture, we said that we should have a stop criteria for the iterations. So initially we pass the maximum number of iterations, and in each recursion we reduce that number by 1 unit, and when it hits 0 we quit, we give up and say that okay, max iterations reached and we couldn't find the root, so the root, we just return a nan, not a number, right? But then we also said that if the root is in fact found, the stop criteria or the convergence criteria would be the value of the function is less than the absolute error. Unfortunately, this is not a good convergence criteria. So what I've done here is that I changed it, I put it here. So after the initial guess, at this step, we calculate the x, the next step, the value for the next step. And then we calculate the relative errors and also the absolute error based on the guess. Or we could have based on the x2. Based on the new value or the previous value, doesn't really matter. But then the key here is that I'm also including the relative errors. So relative error number 1 is x2 minus guess divided by guess. Relative error 2 is x2 minus guess divided by x2. And the reason that I'm using both, because one of these, guess or x2, might be 0. There's a very high chance that we set the initial guess to 0. So if I just use this, division by 0 returns infinity, which is not a good convergence criteria, okay? So we compared two relative errors to the relative error that we set initially for the convergence, and also the absolute error for the absolute error convergence. And if one of these satisfies, then we return guess. And to recap, the absolute error and the relative errors, I've set them to 1e negative 15. Typically, the relative error is reached first, then the absolute error, but sometimes the absolute error may reach first, okay? Now, if you recall, we tried to do we tried to search for all the roots of x times sine of x in the interval of -5 to 10 with 100 sub-intervals and 1000 max iterations for each sub-interval. And we couldn't find all the roots. But now with this new convergence change, with this new convergence criteria, if we run the code, we see that we can find all the 5 roots, 1, 2, 3, 4, 5 roots. 0 minus pi, 3 pi, pi, and 2 pi. And it doesn't care if one of the roots is a tangent root. It doesn't really care, as long as the function is smooth and nicely behaved, has all the derivatives, then the Newton's method is guaranteed to give us very fast convergence. Now let's say I start with an initial guess of now here we were looking for all the roots, but let's try to find one root, which is test number 1. Function is x times sine of x, and I want to find the root with the start guess of max.pi. We know that this function at pi has a 0, right? It immediately gives it, but there is a point that the derivative is 0, and it's about 2.03. So let's start with that. So let's start with a point that the derivative is almost 0. Let's see what happens. It returns 571. So it definitely doesn't return a good value. And that's because if it was exactly 0, then we can't find, the Newton's method completely fails. So we can call this a failure of the Newton's method, because 571 is not a valid root near 2. Okay? Alright, let's put this 1.9 minus pi. So if I set to 1.9, 1.9 is here. So it draws a tangent, it goes here, so 1.9 here, and then it tries to converge to the root. So it could either converge to 0, minus pi, or 0, and we see that it actually converges to I assume if we draw the tangent line at 1.9, it hits somewhere around here, then we get negative slope. And so if we try to get to a point that gives us 0, maybe let's try 1.4 for example. Now it returns 0, it converges to 0. Okay, so this is a much better convergence criteria for Newton's method, and it's pretty fast. Let's head to the PowerPoint. So the failures of Newton's method, one of them is obviously bad starting point. If the derivative is 0 right at the beginning, we cannot move forward, right? So the Newton's method fails. Or the derivative is not defined at the beginning. So I have a function, for example, but the function doesn't have a derivative. The derivative doesn't exist at the beginning. So we might very well be stuck right at the beginning because of the fact that the function doesn't have a derivative. But the function, if the function is a smooth function, well behaved, we definitely have a very fast convergence. Okay, so if the function is not smooth, then we might run into some points, not only in the beginning, maybe at some point during the recursion we might run into a point that the derivative doesn't exist. It doesn't have to be in the beginning, but it might be at some point during the iteration. So that could also make the Newton's method fail. But there's one more thing that we discussed before, is that if I know the analytic value or analytic expression for the derivative function, we should be able to set it analytically instead of numerically calculating the derivative. So let's head to Eclipse. I'm going to create a new interface and call it a real root deriv function. And just like before, I'm going to annotate it with functional interface. Alright, for the compiler to double check that it's a functional interface. And I'm going to have a method double values at some point x. Alright, now this returns an array of doubles, and what I'm going to consider here is that basically value 0 is going to be f of x, values 1 is going to be f prime of x, and values 2 is going to be f double prime of x, and etc. Okay, so at the moment I don't know the length of the return, and the length is determined when I actually implement this interface. If we compare it with the real root function, we had a method called value, and it only returned the value of the function f of x, returns f of x. But now I can return the higher order derivatives also. If I have this, I can go back to the real root class and define also a real root deriv function, from the and call it deriv func. Okay, and then I can overload the constructor. So if I pass the real root function, I use the real root function and then make the deriv function null, which is by default is null. But then I can have another overloaded constructor and pass the real root deriv function, deriv func. And then what I'm going to do is that I set the deriv func and set the func to null. So this way I can check which one has been set by the user. So if user passing the deriv function, I'm going to assume that the user has already analytically return down both the function and the expression for the drift. Now in the Newton's method, what I'm going to do is when I'm here, I try to, so we only need to find the value of the coef, okay? So double coef is basically, let's say 0 right at the beginning. Actually we don't need that, so let's check for deriv function. If deriv func is null, we're going to do this. We're going to find the derivative and then do the recursion. Else if basically func equals null, so one of them has to be null, and then what we're going to do, we don't need to find basically the derivative numerically. So what I'm going to do, I'm going to just call the deriv func, and basically what I'm going to do here, so the func is null, so x1 is guess. We're going to get call the deriv func and values at x1 or at guess, and then this is going to return a double. Let's call this values or vals, okay? And then y1 is vals double y1 equals vals the 0th element, and double coef is vals the first element. All right, and the stuff is the same, so no need to numerically calculate the derivative. So let's go to the test Newton class. We're running test 1. Let's make sure the previous implementation works. Yes, still returns 0. And let's create a third test, test 3, and we're going to run test 3. This time I'm going to, instead of real root function, I'm going to implement the real root deriv function. Deriv func equals new, or maybe I can just say x goes to a new double array, x times math dot sign of x as the first element, which is the function, and the derivative is math dot sign of x plus x times math dot cosine of x. All right, and then we're going to run or maybe let's just call it func. And then here we're going to call the values and then get the first element, so everything should be fine here. Null pointer exception. Oh, okay, so we're going to use the deriv func here, call the values, and then the first. Actually we don't need that, it's just y1, right? So we didn't need to actually call the function again. We can just use the y1 value because y1 was the value of the function. Maybe let's just make it in a explicit way. Okay, y1 is the value of the function, I guess. All right, let's run this. Yes, it returns 0. And let's try the other version that returns all the roots. A list of double roots is root finder dot Newton so -5 to 10 sub intervals, 1000 iterations per sub interval, and let's call it also root. We don't need to make it plural. Yes, it can find all the roots. So 0, -pi, 3pi, pi, and 2pi. As you can see here, I'm passing it the function f and f prime. So maybe let's just write it here as a comment. Analytically defining f of x and f prime of x. So sometimes this is a better option than using the trying to numerically estimate the derivative. Okay, so we can use either of these, and for the previous cases, for the previous methods like the Brent method or the secant or the bisection, we really didn't need to have any need. We didn't have any needs for the first derivative or the second derivative. But for Newton's method and the next method, which is a generalized Taylor method, we do need to calculate the higher order derivatives. So if we have them analytically available, if we have an analytic expression, then we can just use the real root deriv function. If we don't know them, we can use the real root function and then numerically calculate them. Okay, thank you for watching, and I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial, I'm going to continue our discussion on root finding algorithms. And after looking at different root finding methods, let's to recap, we looked at the general lemma of root bracketing, which states that if we have a continuous function and f of a times f of b is negative, or the function changes sign from the initial position of the interval to the endpoint, then it must have at least one root in this interval. So, and this interval is then called a root bracket, which means we have one root in this interval. And we looked at the bisection, trisection, secant, and improved secant method, Brent's method, Newton's method, but there's also another method called generalized Taylor method, which we might look into this method, generalized Taylor method, but it's not a common method. It's rarely used. And so we looked at the binary search, we looked at the trisection, we looked at the secant, improved secant, we looked at the Brent's method, we looked at Newton's method, and now what we're going to do, we're going to look at the comparison of the methods. So let's say we have a polynomial, f of x equals x squared, x minus 2 squared, x minus 3 times x minus 4. So in general, this polynomial has a degree of 6. So it should have 6 roots. And in this specific case, all the roots are real. 2 of them, which is 0 and 2, have a multiplicity of 2. So we have 2 roots at 0, 2 roots at 2, 1 root at 3, and 1 root at 4. Alright? Now the reason I'm looking at the polynomial is because of that if we look at the performance of these methods with respect to finding the roots of a polynomial, then because we know that any function can be locally expanded as a polynomial, this is the Taylor's theorem. Then if we have an algorithm that works fine for polynomials, then it should also work fine with the functions, with the general nonlinear function, as long as the initial bracket of the root is small enough so that we can be able to expand the function into a Taylor polynomial. Okay. Now, one of the first thing that we can do with this polynomial is to visually look at the behavior of the function. Okay, and the way I'm going to do it is like this. So we already know the roots, right? 0, 2, 3, and 4. And the behavior at 0 is 0 squared, right? So it should be something like this black curve, x squared. At x minus 2 squared, it's also a behavior such as like x squared, right? But then the question is it going up or down at 0 and 2? And that depends on the incoming value of the function. So at minus infinity, we know that this term is positive, x minus 2 squared is positive, x minus 3 is negative, and x minus 4 is also negative. So the whole function is positive. So the function at minus infinity starts from the plus infinity and comes down, right? So at x equals 0, the behavior is x squared and it should face up. Now another way is just to look at the f double prime. And f double prime for this term is 2, which is constant. Then the value, and so then the concavity depends on the sign of this rest, the rest at 0, which is positive, right? So if I evaluate this part at 0, it's 4 times minus 3 times minus 4, so it's positive, so the function faces up. But typically for polynomials, I use the first method. I just look at the behavior x squared and I say, okay, it has to either face up or down. And that depends on how the function starts from minus infinity and whether or not it's positive or negative, okay, at minus infinity. So here the function is positive, so it should come here and then goes up again, and then it has to come down again because at 2 it's 0, right? So for it to come down, the behavior of the function at x equals 2 must face up. Okay, so it comes down, becomes 0, and then has to go up again, and then at 3 it's 0 again, so it has to come down. So the behavior of function at x equals 3, which is a linear function, the question is whether it's this way or in the positive way, and here it has to be in the negative way. And you can confirm that by basically finding the value of the function, the rest of the polynomial, x squared, x minus 2 squared, x minus 4 at x equals 3. And this is positive at 3, this is positive, x minus 4 is negative, so the slope is negative. So it comes down, then has to go up again because at 4 it's 0, and you can probably guess that it has to be a positive linear behavior, positive slope. So we can readily look at the behavior of this polynomial. 2 roots, simple roots, 2 tangent roots, so even roots. And if you recall, we mentioned that bisection and trisection are based on pure bracketing and nothing else. So bracketing and binary search or ternary search, so they are guaranteed to converge if there is in fact a root in the initial search for so the limitation here in the bisection and trisection was that the original search interval must also be a bracket. So for example, for this polynomial, if I start from minus 1 to 5, the function is both positive, so it's not a valid bracket to find a single root. But then we said that, okay, if I want to find all the roots, what I can do is to divide the initial interval, even if it's not a valid bracket, into very small sub-intervals and try to run the binary search in each sub-interval. Okay, so here we're interested in finding all the roots. is in finding all the roots in the interval, let's say -1 to 6, which is not a valid bracket, right? But we don't care because we're dividing into subintervals. For the secant, we said that it's faster than bisection and trisection, but there is no guarantee that it's going to converge. For Brent, the same thing, it's faster than secant, but there is no guarantee that it's going to converge. For Newton, it's faster than Brent, and the difference from the difference of Newton with the rest was that in Newton we don't really need a start interval, we just need a start point that is close enough to the root. Okay, so Newton is the fastest. It is faster than Brent, but there is no guarantee that it's going to converge. And we look at some of the cases where the Newton's method failed. Obviously, when the slope becomes 0 at some iteration point. Now the other thing is that bisection and trisection, they fail at even roots or the roots that are tangent, because no matter how small the interval is around the root, you can never have a valid bracket because the function has the same sign about the root, right? So there is never a valid bracket, and these two, bisection and trisection, are purely based on bracketing, so they're going to fail. So if we go to Eclipse and try to test this polynomial with bisection or trisection, we most likely are not going to be able to find the root at 0 and the root at 2. Alright, let's head to Eclipse and try to look at all these different methods. So in the Eclipse, in our demo roots project, I'm going to create a class, test all methods, and I'm adding a main method here. Public static void test1 or test bisection. Test bisection. Okay, so I'm going to first start with the bisection. Now if you recall the way we're going to do it, for bisection we don't need the derivative, so I'm going to use this interface, real root function, and I'm going to call it func, and x goes to x squared times x minus 2 times x minus 2 times x minus 3 times x minus 4. Okay, and then we create our real root object. We call it root finder, new real root, and I'm going to pass in the function, the real root function. And if you notice, I use a lambda expression, which is very convenient. And then I'm going to create a list of doubles and roots. Root finder dot bisection. If you recall, we had a method from start and end, start end with an initial guess, and this one that returns a list, start, end, and number of subintervals. So we're going to search in -1 to 6 and 1000 subintervals, or maybe 100. So if you notice, -1 and 6 is not a valid bracket because this function is positive at both ends. But because we are searching into subintervals, we don't really care if the initial search interval is a bracket. Now let's import the list object from the Java utils. Alright. Now at the end we're going to print the root system.out.println roots, and we are going to also plot the function. So in order to plot it, I'm going to create a MATLAB chart, which is in my mathlib in the plotting package, in the plot package. Fig new MATLAB chart, and let's import it from the mathlib.plot, and then I'm going to create the x values. Double x is I'm going to use the linear space function in mathutils from -1 to 6 1000, and double y, I'm going to apply the function to the array, so I call the array func object, apply func to the x. It's just a simple for loop, and then real function, so the interface is not the same, so I'm going to say t goes to func dot value at t. So this way I use this interface to implement another interface using the lambda expression, which is very convenient. And then we're going to fig dot plot x and y, fig dot plot. So I'm going to write this, plot this with the blue color, and then I'm going to have another plot for just the line that is basically y equals 0. So double x1 is -1 and 6, double y1 is 0 and 0. I'm going to plot x1, y1 with a color of red and dotted lines, and then fig dot render plot, fig dot run with a system exit flag true. So if I test this, it finds 3 and 4 as we expected. It doesn't find 0 and 1 because these are tangents, and in order to show the plot I have to go to the run configuration. Because I'm using a Mac, I have to remove the check for this flag. Now, as you can see, we indeed have 4 roots. One is here, one is here at 0, one is at 2, one is at 3, and one is at 4. And this is basically the same shape as we had here, right? So that's one way of just trying to quickly look at the shape of the polynomial by just finding the roots, also the types of the roots. Okay. So the bisection fails to find 0 and 2, the even roots, because no matter how hard it tries or how many subintervals we have, we can never have a valid bracket for 0 and 2 because they are even roots. The function doesn't change sign, right? So let's try trisection. So test trisection. Instead of bisection, I'm going to call test trisection, and here I'm going to call the trisection method with the subinterval. So -1 to 6, 100. Again, trisection and bisection run based on the same philosophy of root bracketing, so this also should fail to get the 3 and 4, 0 and 1. So we only can find 3 and 4, which are simple roots, right? This is a simple root, this is a simple root, this is a tangent root, an even order, and even order. So it fails. So bisection and trisection so far fail. And the next is secant, which, if you recall, we improved it. So test secant. And here I'm going to call the secant method. We have two, one with the start and end that returns one double value, and one with a start and end and number of subintervals that returns a list of roots. So -1, 6, 100. So the secant here also fails. The behavior of the secant is really not, we cannot say for sure whether or not it fails or it fails at the even roots. But what happens if we increase the number of subintervals to 1000? It still fails. So it appears that the secant fails here no matter what. What if we change the interval -2 to 6, 0, 2, 3, 4? Now it can find 0 and 2. And so it appears that the success of the secant method is not guaranteed at all roots, no matter how many subintervals we have, and it mostly depends on the initial interval that we search for the roots, which is not good, because all we want is to start with an interval that has all the roots, and the method should be able to find all the roots, which we definitely see that the secant is not able to find all the roots in the -1 to 6 interval. If I increase it to -4 to 6, it is able to find the root, all the roots. So one negative point for secant for not being able to find all the roots over -1 to 6. So after the secant, we're going to test Brent. Now Brent is one of the good methods, so we have a lot of hopes for Brent in the fact that it should easily be able to find all the roots. Let's see. So here I'm going to do this Brent. We have 3 methods: start, end, number of subintervals, start, end, and guess. So this one returns all the roots, -1 to 6 with 100 subintervals. Yes, it is able to find all the roots. As you can see, it doesn't find them in the sorted order, so it finds 0 first. So it finds 0, and then finds 3, and then finds 2 and 4. But it's able to find all the roots. So even if I change to -4 to 6, still the same, 0, e -9, it's basically 0, and then 1.99, this is 2, and then 3 and 4. So Brent is the best. And let's look at the Newton. Test Newton. We also have a lot of hopes for Newton because it's a fast algorithm and it doesn't care about the bracketing or any of that stuff. So we hope that it's also going to find all the roots just like Brent, and even faster. So here I should call the Newton method start, end, subintervals -1, 6, subintervals 100, and max iterations I'm going to set them 1 to 100. Unfortunately, the Newton fails to find the 0 and 2, which is very displeasing because we had a lot of hopes for the Newton's method. What if I increase 1000 subintervals? No, it's still not able to find. And what if I set to -2 to 6? It's still not able to find all the roots. -5 to 6. No, it's still not able. 1000 iterations, still not able. So unfortunately, Newton also fails in this test to find all the roots, and that's very unsatisfactory. Let's go and have a look at the Newton's method. If you recall, in the Newton we have 2 relative errors and the absolute error for the convergence test, and apparently none of them can succeed in resulting in the finding the roots. What if we right now we're using absolute error and relative error of 10 to the negative 15. What if we set it to 10 to the negative 12? Let's see if the Newton is able. Now it can find 2, 3 and 4. It still cannot find 0. So if we reduce the relative error to 1e10, so 4, 3, 2, 2, 2, 2, 2. So now it's able to find 4, 3, and 2. And obviously we see some repetition here, which is expected because we have multiple subintervals that may converge to the same root. But it still cannot find 0. So Newton really fails compared to Brent here. So what we conclude here is that although Newton could be in fact faster than the rest of the methods, but Brent seems to be most reliable for this type of cases. So I'm going to head back to real root and set the errors to 1e15. Okay? So let's try Brent one more time. It is able to easily find all the roots. So my recommendation is try to use the Brent method or try to add more convergence or test to the Newton method to make it more reliable. Thank you for watching, and I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial I'm going to finish up our discussion on root finding algorithms. So one last thing that remains from root finding algorithms is the generalized Taylor's method, and it's based on two facts. Fact one is that it is easy to find the roots of a polynomial, and we have general methods such as Laguerre's method that can provide all the roots of a polynomial. Okay? And fact number two, any smooth function can be expanded into a polynomial about a given point. Okay? We've seen that. We have implemented the Taylor expansion in Java before. So if you're not familiar with Taylor expansion, you can just look at one of my tutorials on the Taylor expansion method and its implementation in Java. So how does the generalized Taylor's method work? It works based on a few steps. Step 1, find Taylor expansion at an initial guess of the root over a given interval. Okay, so if you have an interval and it's a valid bracket for the root, then you can pick one point, for example the midpoint of the interval, and then find the Taylor expansion of some degree, first degree, second degree, third degree at that point. Okay, and then yes, obviously we assume that the initial interval brackets the root, and then after finding the Taylor expansion, which is a polynomial, find the x-intercept of the Taylor polynomial, which is another way of saying find the real roots of this polynomial. Okay, and then because we're interested in the roots in the given interval, only keep the real roots of the polynomial that actually lie in this interval. Okay, and then perform a recursion by finding the Taylor expansion and the new x-intercept. So find the real roots in the interval, and then we also have the start and the end of the interval and all the roots in between. So find the valid bracket again, and then in that bracket do the recursion. So pass the start and end point of that bracket, that new bracket, based on the roots of the polynomial to the function, and then it automatically goes in, creates the Taylor expansion, find its real root, and then continues until it finds the root. Okay, so if we have a Taylor expansion of 1, which means at each point at each step we're finding the tangent line to the plot, to the function f of x, and then finding its x-intercept. This is exactly Newton's method. So you can imagine that if Newton's method, which is basically the very special case of degree 1 Taylor expansion, has a quadratic convergence, higher order Taylor expansions can have much faster convergence, okay? And now obviously if we want to do Taylor expansions of more than first degree, second degree, third degree, we need to have or calculate the higher order derivatives of the function, second derivative, third derivative. So one way is doing the numerical estimation. We looked at how to calculate the first derivative numerically, but there are also expressions for calculating the second derivative, third derivative, etc. Right? But there are also other ways. One way is to use the real root deriv function interface that we implemented. This forces the user to not only give the expression for f, but also the user should also give the expression for f prime, f double prime, etc. Because if you recall, real root deriv function returns an array of double values. The first one is the f, the second one should be f prime, the third one should be f double prime, etc. So that's one way. So the programmer asks the user to actually provide these functions f prime, f double prime. That's one way. The other way is to use our symbolic function space that we developed in some of the previous lectures, and then we can construct the function from the basic functions, and the basic functions have analytic expression. So that's another way of finding all the higher order derivatives. Okay. Now, besides all these ways of the ways that we discussed and implemented all these root finding algorithms, there are also other already available libraries that you can use to find the roots. You don't need to write all these algorithms by yourself, which I highly recommend you do that. So just follow my tutorials and try to implement and even improve all these root finding algorithms, okay? But if you don't want that, if you want to just use already available libraries, which are good libraries, one of them is from Michael Flanagan's Java Scientific Library. We discussed this before in the polynomial tutorial and also in the complex numbers tutorial. So you can find it, you can find the Java archive file and download it from Michael's website, www.ee.ucl, University College London.ac.uk/m/Flanagan/Java. And there is a complete Java document on the website with all the explanations of all the methods and all the classes and all the packages, okay? Now this is a snapshot of how this Flanagan library looks like. So it has a couple of packages, and one of them is called roots. And in this roots, it has 3 classes. 2 of them are interface, and one of them is the main class that implements all the algorithms. And it's exactly similar to what we already developed so far during all these lectures. So it has a real root class, which is an interface, a functional interface, and defines a real valued real function. So you supply a real double value and it returns a double value for the function. And there is another function in functional interface, real root deriv function. So this has a deriv in the name, real root deriv function, exactly like what we implemented. And it basically defines the function and all its derivatives. So it returns an array of double values. Finally, we have a real root class that again implements all the basic algorithms, bisection, Brent, Newton-Raphson. And there is another method that it implements. It's called false position method. And if you look this up, false position, on Google or go to Wikipedia and search it. It's basically our improved secant method. So that's another name for improved secant method, false position. All right. So the structure of roots package in Michael Flanagan's library is exactly the way we implement it. Now, regarding the false position or the secant method, just to refresh your memory, if I go to the secant method, when we discussed secant method, I mentioned that the original method is a recursion that says that, okay, start from x0 and x1, which should be a bracket of the root, and then connect the line, connect the two start point and end point on the function, and the x-intercept, or the point that it crosses the x-axis, is guaranteed to be between x0 and x1, okay? And then the idea of the recursion was that now take x1 and x2, the new crossing, as the new interval and continue to find the x-intercept. The problem was that if you just do this simple recursion, the x1, x2 might not be a bracket for the root, which we see it here, right? So the idea of the improved secant method, which is also called the false position method, is that instead of doing the recursion like that, be some intelligent, and instead when we find a new crossing point, xn, test for the bracket, test whether or not xn x minus 1 is in fact a bracket or not. If it's not, then xn x minus 2 is the bracket, and we should connect them instead of this line. And this also guaranteed to fall between xn minus 2 and xn, so we're getting closer and closer to the root, okay? So it just says that be more smart about the way you implement the recursion. All right. Now there is another a good point or a good algorithm in this real root class, which also basically allows for automatic extension of the original interval. What does it mean? It means that if we set the original search interval as a, b, it finds the half length of the interval b minus a over 2, okay? Now what it does when we call one of these methods is that it tries to first determine whether or not this initial interval is a valid bracket or not. If it's the valid bracket, then it continues with the method. But if it's not, it tries to extend the interval, the AB interval, into a minus dx, b plus dx. Okay? So it adds half the interval to the lower bound and upper bound. And there are flags that you can set whether or not you want to extend the upper bound, lower bound, or both of them, or none of them. And we'll look into that, okay? So that's another interesting thing that we can implement and try to extend the bounds of the initial interval if it's not a valid bracket. So let's head to Eclipse. Let's try to decompile this real root class and look into all the methods. So if you go to my mathlib library and go to the reference libraries, we have the flanagan.jar. In the Flanagan we have the roots, and in the roots we have real root function, which is a functional interface, has one abstract method function, and it takes a double value and returns the value of the function, okay? And we also have real root deriv function, which returns an array of doubles. So the 0th element is the value of the function, the first element is the derivative, first derivative, the second element is the second derivative, etc. Okay? And then we have the real root. Now in the real root we have a couple of private fields. One is originally the root is double.nan, exactly like what we did. We have some tolerance. This is, I believe it's used for the convergence. We have maximum number of iterations, and iter n, which I believe is used for the number of iterations in the Newton's method. and then upper bound and lower bound of the search, the estimate of the root, maximum bounds extension. This determines how many times, the maximum number of times that we can extend the bounds. No bound extension, this is a flag that if we set it to true, the methods don't try to extend the bound if the original interval is not a valid bracket. No lower bound extensions, no upper bound extensions. So if we set one of these to true, then only one of the bounds of the initial search interval is extended. Suppress limit reached method, return none, which we said it's a good idea to always return none. Suppress none message, a static iteration max. So this is basically, not only it has all the methods, it also implement them as static methods. You see Brent static, bisection static, false position static, Newton-Raphson static, and also the roots of the polynomials. Okay, so it's also always a good idea to implement the methods as static methods. Then we can directly access them and pass any function. No static bound extensions, no static lower bound extensions, no static upper bound extension, static return none, real tolerance 1 e minus 14. So this is the actual or real tolerance that it uses to see whether or not the root has been found. If you recall, we set it to 1 e negative 15. So here it's set to 1 e negative 14. So there are some setters for all these, most of these parameters: set lower bound, set upper bound, reset non exception to true, reset non exception to false, suppress non message, suppress non message, and allow non message, set estimate. So you can just use this to set the global estimate of the root, set tolerance, get tolerance, set iteration max, get iteration max, get iter n, set maximum static bounds extension, no bounds extensions, no lower bound extension, no upper bound extension, suppress limit reached method, suppress limit reached method, Brent. So this is where the algorithms start. So the first one is Brent method, which takes a real root function and then calls the general Brent method that has a real root function and the start point, the start of the interval, and then the end of the interval. So var2 is the start of the interval, var4 is end, and var1 is the actual real root function. Okay, so when we call this, it sets the lower bound to var2, upper bound to var4. And the first test here is whether or not the upper bound and lower bound are equal. And as I mentioned before, the exact equality is not recommended with double numbers. It's always best to compare them with the tolerance. But here it's using exact equality. And if the start and end of the interval are exactly the same, it returns or throws an exception, illegal argument exception, and says that upper cannot equal lower. Okay, so this is the first test that we should do. The second test is here. So if the var2 and var4 are not the same, then it tests whether var2, which we assume to be the start of the interval, is in fact less than var4 or not. So if var4, which is the end, is less than var2, it just swaps the values of the var2 and var4. Okay, so it just ensures that the start point is always less than the end point. Not equal, it's not equal, and it's always smaller, which is really not required for bisection or trisection method, but for Brent, it just tries to make sure that the start point is less than the end point. Okay, if it's not, it swaps the values. So var7 is just a intermediate variable here that first holds the value in var4, and then we copy var2 to var4, and then copy var7 to var2. This way we swap the values of var2 and var4. Okay, So this is the second test. And then it finds the values of the function at the start point and the end points. var9 and var11 are the function values, and then tests if one of these values is nan, which most likely is not going to happen for our functions, but in a rare case that the function actually returns a nan, it tries to catch this and returns a message that, okay, function is nan, I cannot do anything, I cannot proceed, so it just returns nan as the root. Same thing for so this was for the lower bound, and the next is the upper bound. The function at the upper bound is nan, okay? Next, it tries to find the half length of the interval. var15 is var4 minus var2 over 2, so it's the half length. And it sets a flag var3 to true, and var3 is basically for the flag for extending the lower bound and upper bound. So it finds half length, this flag is true, so it goes into this while loop, and then it tries to look at the bracketing. So var9 is the function value, var11 is the function value at the other end. So if the function value at two ends is less than or equal 0, it's in fact a valid bracket. So it sets the flag to false, which means then we just come out of the there is no need to extend the bounds, okay, of the interval. It just sets the flag to false, and then the while loop terminates. But if it's not a valid bracket, so if var9 times var11 is greater than 0, it tries to extend the bounds, lower bound and upper bound. So if no bound extension flag is set to true, it says that, okay, I cannot extend the bound and the current interval is not a bracket, so just return nan. But then if this is basically false, so we allow for the extension of the bounds, then it increases this integer variable, which is 0, which keeps track of how many times the bounds have been extended, because we have this variable maximum bounds extension, which I believe originally was set to 100. So if we haven't reached the maximum number of bound extensions, then what happens, it subtracts the half length of the interval from the var2 and then updates the value of the function at the new lower bound. Similarly here, it adds the half length to the endpoint and updates the value of the endpoint and updates the value of the function at the new endpoint, and then the while loop continues. So this is this whole thing, this whole while loop is for extending the bounds in order to get a valid bracket, okay? And then now it gets the valid bracket, then it has two other tests. One is the value of the function at the start point of the bracket and the value of the function at the end point of the bracket, and it tests whether or not the start point and the end point is in fact the root. If it's the root, it sets the root to the value and then basically returns. Okay. Now, if you recall, we in fact implemented this as one of our stop conditions. If we go back to our roots, to the real root, for example, for bisection, we had this. We checked for the value of the function at the start, less than absolute error. And again, it's not recommended to use exact equality with double numbers. It's better to have a tolerance, which we define as absolute error. But then we also looked at the relative error, because eventually the iteration creates a sequence of numbers that we hope to converge to the actual root. And for the bisection, it is guaranteed to converge, but it's pretty slow. or it could be slower than the other methods such as Brent or Newton. Okay, so these two tests, let's say these two tests fail, so the start point and the end point of the interval are not the roots, then it goes into the iteration. So what it does, it finds the midpoint as the guess, and then finds the function at that value of the function at that point, and then does the iteration. And this is how it implements the iteration for the Brent method. So a start point, end point, and we need another third point, which was our guess, and here it's set to the midpoint. And while var6 is a flag that sets the termination of the Brent's algorithm. So if it goes into this recursion, the first thing that it tests is the stop condition of the recursion. The stop condition happens when as long as the value of the function var23 is basically the value of the function. As long as this value is larger than the tolerance, we continue, and then here is where we actually do the quadratic polynomial interpolation, and it continues until it terminates, and after that the root is set. And there are also other flags, other checks for the maximum number of iterations, and eventually it returns the root. So as you can see, this is not exactly the way we implemented Brent's method. We just so here it's not using the recursion in its method calling way, right? Calling the method again and again creates a stack of methods in the execution chain. But here it just puts everything in the while loop and updates the values of the variables instead of calling the method over and over again. So if you recall, for example, in the Brent method that we implemented with the start and end and guess, we just go into the Brent again and again. So this creates a stack or a chain of method callings, and eventually once it terminates, it comes back up. So this, when we use recursion, it makes the code much cleaner, but we have some performance hit because of this chain of method callings that we have to go deeper and deeper and then coming back. So while loop could be in fact more efficient, but it makes the code a little bit more complicated and longer. Okay? Now after Brent, we have the bisection method, which is the most simplest. So we have the function and the start point and end point. Obviously the first test is checking for the lower bound and upper bound being equal, which is not allowed, and then we test whether or not the start point is in fact less than the end point. If not, we just swap the variables, we swap the values, and then we have the same thing here, value of the function at the start point, var9 and var11, value of the function at the end point. If one of them is none, we return none, and then we go into the while loop for extending the bounds, a lower bound, upper bound, and after that we check whether or not the start point or end point is the root. If not, then we go into the bisection and the binary search, and the binary search is basically this part. So var23 is the flag for checking when to end the iteration, and then when var7 is less than tolerance, we just call var24 as the root, and initially the initial guess is the midpoint, var2 plus var4 over 2. It's the midpoint of the of the interval, just exactly like we did. We said that, okay, the initial guess is the midpoint of the interval. Okay, so this is one condition for termination. The other one is that once it does that var24, and then it checks for the brackets, and this is the recursion. So what it does is looks at the looks at the var21, which is the value of the function at the midpoint, and check it by the value of the function at the endpoint and the value of the function at the start point. Okay, so if this is not a bracket, it sets the var4 to var24, so it goes into the second half, and if it's true, it goes into the first half, and just it continues var24 var2 plus var4 over 2, and eventually this way it does the recursion or the binary search. And again, using the direct method recursion, so basically it does exactly this. So it looks at the two brackets, start to the midpoint, at the midpoint to the end. One of them is the valid bracket, and then it goes does the recursion in that bracket. As you can see, our code is much cleaner and readable, but it uses the method recursion, which has this stack of the methods and has some performance hit because of that. Next is the false position, which is our secant method. Again, the same test for the equality of the lower and upper bound, swapping the values for extending the bounds, which is this while loop, and then checking the initial and end points as the roots, and then the actual secant implementation. And in the secant, let's bring up our code. We have the start and the value of the function at the start and the value function at the end, and then we find the inverse of the slope of this line that goes from the start to end, and then we do the recursion. Okay, here's the same thing, var4 minus var2 divided by var11, which is the value of function of var4, and var9, which is the value of function at var2. Now this implementation is a bit different because here it uses the plus sign, but if you look into the details, eventually this is equivalent to what we did here. Now the reason it tries to implement it in this way, because then we avoid the case where this denominator becomes 0, because the only way that this denominator can become 0 is when both of these absolute values are 0. But if one of these is 0, we already have these checks for termination. So if this checks fails, means that this denominator is never 0. So this could be a better or safer way of implementing the secant method. And this continues until it finds the root and returns the root. Now there is another method here called so we have the Brent, we have the false position, we have Newton-Raphson, and again the same story, checking for the start point and the end point, and then doing the extension of the upper bound and the lower bound, and then eventually finding the root. For the Newton-Raphson, the root happens here. Basically it finds the slope of the function, so it calls the real root deriv function. It assumes that the user has already provided the function with the value with the derivative function too. So var9 here is the var11, so this is var11, and var11 is basically the 0th element is basically the value of the function. The first element is the value of the derivative. And if you recall, in the recursion of the Newton's method, we have the previous value minus the function divided by the derivative of the function. That's why we have var 11 0, which is the function, divided by var 11 number 1, which is the derivative of the function. And then it checks whether or not the value of the function is in fact 0. If it's not, and then the it updates the value, the iteration, which so it finds this fraction, this number, and then subtract it from the original point, and then substitute it in that variable. So var1 is the variable that is keeping track of our iterations. Okay, so basically it calculates this, subtracts from the number, and substitute it into the number itself to be able to do the iterations. So this is where the actual iteration happens. And if you recall, in our method, the way we implemented Newton was to call the Newton method again with the updated value. If you don't want to do that kind of method recursion, you can just simply do this with a while loop. Then you must have a while loop so that you can set a flag var 7 for termination. Okay? Now there are also other methods. Bisection Newton-Raphson, which tries to combine the bisection. Basically, you give, instead of having a double value as the initial guess, you give the start point and the end point. So it runs the bisection first to find the value. The idea here is like this. The bisection Newton-Raphson is, you give the start and end point of the interval, and it tries to run the bisection first to find a bracket for the root. Once you have the bracket, it goes into the Newton iteration. Okay, so it's a combination of bisection and Newton-Raphson. And there are also some other methods for setting some of the other global variables. And then all these methods, Brent, bisection, are also implemented as a static method. So these are class level methods, and you pass the real root function, and then for Brent, for example, we need 3 points, and it basically copy and paste of the previous methods, but here these are static methods, so we can directly access them with the class name. Bisection, we have 3 points, start, end, and the initial guess. False position method, we have 3 points. Bisection Newton-Raphson, we have 1 2 3. Newton-Raphson, we have 2. And then it also has methods for polynomials, so quadratic polynomial, and these are the coefficients. var 0, var 2, var 4 are the coefficients of a quadratic polynomial, and it returns the roots and also mark them with complex or real. And basically what it does is, for quadratics, it's very simple. It calculates the delta function, and then basically the discriminator of the quadratic equation, b squared minus 4ac. var 2 is b, var 0 is a, and var 4 is c, and checks whether or not it's negative or positive. If it's negative, we have 2 complex roots, and it calls the complex polynomial to find the complex roots. Otherwise, it just finds it's just the basic algebraic math, and all the roots are real. The same thing for cubic. It calculates the discriminant of the cubic polynomial and tests whether or not it has complex roots or not. If it has, then it calls the complex polynomial object and calls the cubic method. Otherwise, it just directly implements the algebraic equations for the roots. And there are also other methods for polynomial roots of polynomials. You give an array of coefficients and an initial guess. Yeah, that's it. So this is the roots package in Flanagan's library, and these are very good methods. I highly recommend them and recommend that you use them. I also recommend that you follow my past tutorials on root finding algorithms and try to implement your own libraries. That gives you more flexibility in terms of modifying them, improving them. So this is the conclusion on for now at least, it's the conclusion on all the root finding algorithms. Next, we are going to look into some optimization methods. Thank you for watching, and I'll see you in the next video.